The mid-50s, a time of exuberant change. From the Depression of the 30s, the nation had plunged into the strictures and rationing of World War II. Now, for the first time in decades, Americans were enjoying a booming economy, and they ate it up. The jet age had arrived, and Americans were fascinated with the sleek new swept-wing fighters that had cleared the skies in Korea and broken the sound barrier in level flight. Our great national icon, the automobile, reflected their style. It was the era of poodle skirts, hula hoops, and hydrogen bombs. Behind the fads and conspicuous consumption, perhaps fueling them, lay a dark specter. Our World War II ally, the Soviet Union, was now an implacable enemy, and they had the bomb. The space race was on. The US and Soviet Union were developing missiles to deliver nuclear warheads and to place payloads in orbit. The Soviets were ahead at the first lap. Sputnik, barely the size of a soccer ball, carried only a simple transmitter, but its monotonous beep sent a chilling message. Soviet test sites lay deep in a gigantic and seemingly impenetrable landmass. The US was desperate for intelligence on these threats. A gawky, highly specialized U-2 could overfly the sites at 80,000 feet, but its slow speed and agonizingly long loiter time made it increasingly vulnerable to improving Soviet air defenses. It was only a matter of time. The US government needed a better reconnaissance platform. By 1956, Lockheed was designing such an aircraft, the CL-400. Pratt Whitney was selected to develop a radical new engine, the liquid hydrogen-powered 304. This highly classified project was codenamed Suntan. At the same time, the U.S. Navy was fighting an advanced attack plane, the Mach 3. It demanded an engine with far more thrust than any yet existing. Pratt & Whitney was approached to create a powerful new turbojet, the J58. Dick Core was chosen as chief engineer for both projects.
Suntan was a project to develop a hydrogen-fueled fan for very high-altitude operation, about Mach 2 at 100,000 feet. And the engine was a concept invented by a fellow by the name of Ray, I think that was R-A-E. And he convinced the Air Force that this was the right kind of engine to use at very high altitude. But he had no facilities for developing an engine, and the Air Force turned to Pratt & Whitney to develop this engine, which we call the 304. And at the same time, we had another project. I was assigned another project, which was the J58 for the Navy. And the Navy at that time was very interested in using what's fuels that were doctored with boron.
Development of these new engines began in East Hartford, but it quickly became apparent that the Connecticut facility possessed neither the space, the noise containment, nor the security to see the programs through. The search for a new site led to a tract of land in the northeastern part of Florida's Everglades. The remote location near West Palm Beach was ideal, except for swamps, mosquitoes, alligators, and rattlesnakes. In 1957, a contract was signed for construction of the new facility, and Pratt & Whitney's Florida Research and Development Center was born. Initial development was daunting. There was no direct access to the 7,000-acre site. The state of Florida agreed to build a road, the Beeline Highway, but the segment from West Palm Beach to the plant was delayed when the Loxahatchee Slough refused to cooperate. It swallowed tons of fill and 2 bulldozers. Designer Ray Schneider was one of the first employees hired specifically for the new facility.
Well, the first 6 weeks I was down here, the Beeline Highway wasn't open because of a quicksand problem, and they couldn't build a section of the road. So they routed us through the swamp on a dirt road, and it was very interesting because it was hard to have two cars pass at the time. The road was so narrow.
After more tons of fill and months of work, the beeline was finally completed. Plant construction was nearly as difficult. Unusually rainy weather turned construction sites into a sea of mud. Fill for building sites came from borrow pits, adding numerous new ponds and lakes. Environmental concerns led to creating new wetlands to replace those being filled for construction. Charles Rolke, the first general manager of the new facility, faced a number of obstacles. Pratt Whitney was unwilling to part with experienced support personnel from Connecticut, and much of the workforce had to be recruited and trained locally. At the same time, the customers wanted work on the 304 and J58 to progress as quickly as possible. Construction was barely underway when J58 and 304 engines began arriving from East Hartford. Work on these projects advanced rapidly in makeshift rented shops. First permanent structures completed were the test stands. The Air Force built two facilities to generate liquid hydrogen for the 304. They were codenamed Mama Bear and Papa Bear, and for security reasons they were given a cover story. Local residents were told they were processing plants for the Apex Fertilizer Company. Despite the primitive conditions, spirits were high. A young engineer, Frank Maccabee, was part of that original cadre.
A group of us, about 30 or 40 engineers and their families, had been transferred down from Hartford. All of us were young. The test engineer group, of course, we had a management team as well, but our families were young. This was an area that had not been developed at all. The communities were practically bare of houses. As a matter of fact, a whole new community was built in Lake Park, where I live, and we were one of the first families to move in there. Everything was new, including the technology, the challenge, the relationship with the customer, the facility itself. It was all very exciting, and we were all eager and didn't know that we couldn't do some of the things that actually were accomplished, and we just had a lot of fun. There was a tremendous camaraderie.
A year before the main office building was complete, both engines were ready for testing. In September 1957, the primitive quiet of the swamp was shattered by the roar of the first 304 test run, a thunder heard for miles under sunny Florida skies. The J58 too progressed well for the Navy, and the engine made its initial test firing on Christmas Eve, 1957. On May 27, 1958, the Florida Research and Development Center was officially dedicated. The new Florida Facilities Direction may have seemed clearly defined. The nation's was not. Within the next 5 years, we saw the election and endured the assassination of a young new president, watched the communist takeover of Cuba, and sweated through the ensuing missile crisis. We held our breath as tiny Friendship 7 carried 41-year-old John Glenn into history as the first American in orbit. We watched the slow expansion of American involvement in a remote Asian country, and honored the call to place a man on the moon by the end of the decade. Pratt & Whitney faced its own unique challenges. In the early stages of the 304 program, skeptics feared that liquid hydrogen would never be safe. The mere mention of it conjured up visions of the Hindenburg disaster. But Pratt & Whitney devised efficient new ways to handle this volatile fuel, and the 304 proved safe and successful. Both programs were progressing on schedule. Then came a strange musical chairs change. The Navy lost interest in developing their Mach 3 attack plane, and work on the powerful J58 ground to a halt after just a few test firings. At the same time, things were going badly for the Air Force's CL-400 program. As designed, the aircraft presented support problems, was based on technology already becoming obsolete, and could not carry sufficient fuel for the needed range. The Air Force decided to start with a clean slate and canceled development of the CL-400. Work on the 304 hydrogen engine was suspended. Setback was brief. Pratt & Whitney's new expertise and new facility were just beginning to blossom. The U.S. still required a long-range reconnaissance platform. The Air Force and CIA recruited legendary aircraft designer Kelly Johnson and the super-secret Lockheed Skunk Works to design a new plane, the A-11. To meet the demands of high-altitude Mach 3 flight, they turned to Pratt & Whitney's new J58 as the most promising engine candidate. At the same time, the need for space launch capabilities was growing rapidly. The Air Force enlisted Pratt & Whitney's newfound expertise with liquid hydrogen to develop a compact, powerful upper-stage booster engine, the LR-115. In 1961, the program was transferred to NASA, and the engine became known as the RL-10. The last contractual 304 tests were still underway when RL-10 development began. The company never missed a beat.
I had the good fortune of being the test engineer responsible for assembling and testing the first RL-10, which we called F-121. It was a new technology. Hydrogen and oxygen had never been used as a rocket fuel before in any quantity. The cycle that the engine was based on was new, the bootstrap cycle. The materials that we used were used for the first time in this environment. It was just all new and exciting. I remember the first time we fired the RL-10 was on third shift. It was the middle of the night in the swamp. It was black as ink, a starry sky, and when that engine lit off, it was like doomsday had arrived. A tremendous sheet of flame out the diffuser, a noise that you just never heard before, at least I hadn't. It would actually get into your lungs and breathe for you. It was just tremendously exciting. And the engine ran and ran and ran and ran. As a matter of fact, I believe it was 426 seconds, which doesn't sound like long, but at that time it was the longest duration firing of any rocket engine anywhere. We had set a new record that night.
While things went well for the new RL-10, adapting the J58 for the A-11 was not as simple as anticipated. The technical demands of sustained Mach 3 flight were daunting. They required not just new designs, but completely new concepts. A brilliant engineer, Bob Abernathy, devised ducts that allowed inlet air to bypass the compressor in supersonic flight. This simplified the inlet design, and at high Mach numbers, virtually converted the engine from a turbojet to a ramjet.
The engine structure had to stand these very high pressures at 1,500 degrees Fahrenheit, bottle temperature. That melts most things. The lab found a way to make it possible to weld what we used to use for turbine blades called lost boy in sheet structure.
If the J58 had to operate at temperatures beyond the tolerance of available metals, there was a simple solution: do the impossible and create new ways to process previously unusable alloys that could do the job. Joe Moore was a young materials engineer when he was faced with these challenges. Considering the complexity of the task, his first exposure to the materials laboratory was disconcerting.
Well, shortly after I came to work, I looked at the situation. I thought, my God, we're not a development lab, and that was why I'd been brought there. However, the guy that brought me said he wanted to make it more of a real development laboratory, and I looked at it, and then I thought, my gosh, this place is just a control lab. They check pieces that come in and raw stock that comes in to see if they meet the mechanical and chemical requirements, and that's about it. And so I truly did this. It sounds corny, but I made up my mind that I wanted to see us become the best laboratory in the world.
Design of the A-11 at Lockheed faced similar challenges. At Mach 3, portions of the aircraft skin would reach temperatures of nearly 1,000 degrees, well above the melting point of conventional materials. Kelly Johnson's engineers turned to Pratt & Whitney's pioneering work with titanium alloys for the answer. The next few years of RL-10 and J58 development were fraught with difficulties as FRDC delved into the unknown. Dick Mulready was a driving force behind the new science of cryogenic fuels.
Hydrogen is an excellent working fluid, which means that it doesn't take much of it as a flow material through a turbine to generate a lot of power. And because it was hydrogen, we could take the hydrogen that was going to be burned in the cool thrust chamber, and the heat that it extracted from the thrust chamber was enough to drive the turbopumps. So the hydrogen flows through the pump, around through the cooling jacket, and then up into the chamber. So all of it is used, nothing is wasted, there's no gas generator that throws away anything. And so it's an elegant sight. It really is perfection. And it's the reason the engine has now lasted over 40 years. It's the longest living mark Pratt Whitney for an engine. Well, we took the engine, which had been run horizontally, put it in a pair up in the E5 stand, and made a firing one day. Al Gardner was with me. He was the Air Force project officer, and everything worked fine. The next day, there was a second firing on the E5 stand, and there was an explosion.
That second firing was eagerly attended by a group of NASA officials, led by the renowned German rocket scientist Wernher von Braun. William Missimer was a young instrumentation engineer who witnessed the event.
We pushed the button for the run, and all these dignitaries were there, and the stand blew up. I mean, not a little blow up. This was a big blow up that lit up the sky, and it was a 1,000-foot plume went up. And we all turned pale. And I could hear von Braun saying, "Oh, shit." He turned around and walked out. Well, that led to a very long but wonderful episode that had a happy ending, where that place turned to and found out why that problem happened. It was an ignition problem. And believe it or not, all previous tests, we had the RL-10 was laying horizontal, and it ignited very, very reliably. When you put it in a vertical position, you got the wrong mixture ratio for ignition. One lit and the other one just put down into a common exhaust, unburned propellants, and it went off like a bomb. But getting to that answer was one of the most exciting technical witch hunts I've ever been through.
The RL-10's ignition problems were ultimately solved, and the engine passed its preliminary flight rating test in January 1962. The J58 passed its preliminary flight rating test just a few months later. Under a cloak of secrecy, flight testing of the A-11 progressed rapidly, and an experimental interceptor version, the YF-12A, entered operational service. A reconnaissance version became operational in January 1966, the legendary SR-71 Blackbird. Though now retired from the U.S. Air Force, the SR-71 still holds numerous speed and altitude records thanks to the J58. 2,193 miles per hour in level flight, and sustained level flight at 85,069 feet. In 1990, it flew from Los Angeles to Washington, D.C. in 1 hour, 4 minutes, and 19.89 seconds. The RL-10 was also about to make history, but not without some tense moments first.
The first launch, of course, was disastrous because the Atlas launch vehicle suffered a failure on liftoff and exploded essentially on the pad. There's a funny story about that. One of our people was in the telemetry shack at the Cape, and his job was to monitor the telemetry from the engine during the launch and report back to Bill Gorton, who was the vice president general manager down here then, what kind of performance we were seeing from the engine once it fired in space. So the Atlas fired and lifted off about 3 feet off the pad, and the sustainer engine shut down, and the vehicle slowly settled back down into the launch pad into a tremendous explosion. You can imagine how big a fireball that much hydrogen and oxygen makes. Well, the telemetry package on the Centaur vehicle, the upper stage, which our engines were on, was battery powered, and it was external to the vehicle. And when the explosion occurred, it was blown free of the vehicle into a field about 300 yards away, and it lay there radiating. It was still sending out signals. Our fellow in the telemetry shack was watching those signals on a trace on an oscilloscope, and it didn't show anything other than that everything was normal. The engine, of course, hadn't fired at that time and wasn't supposed to, so all the traces were flat and looked normal. So he was reporting back to Bill Gorton and the rest of the management group down here that everything was fine. In the meantime, the vehicle was a smoking pile of rubbish on the launch pad.
Finally, in November 1963, 2 RL-10s successfully boosted a Centaur upper stage into orbit.
Again, a group of us had gone there somewhat apprehensive because we had had so many problems in the past, and this launch was picture perfect. Everything went according to schedule. And when the telemetry traces showed that the RL-10s had fired right on schedule, the chamber pressure came up and held constant right where it was supposed to, it was the greatest feeling you can imagine.
2 months later, the 6 RL-10s of a Saturn S4 stage propelled a 37,000-pound payload into orbit, successfully demonstrating the practicality of hydrogen-oxygen fuel for the Apollo Moon exploration program. The RL-10 went on to set the standard for performance and reliability in upper-stage propulsion systems. It boosted 7 surveyor missions to the lunar surface in preparation for Apollo. It powered Mariner and Pioneer to our neighboring planets, and sent Voyager to the farthest reaches of our solar system and beyond. The success of the RL-10 and J58 quickly led to other pioneering programs. FRDC began development of a high-pressure rocket engine quite different from the RL-10. Instead of an expander cycle, the engine used a pre-burner to drive turbopumps delivering the cryogenic fuels. It had tremendous growth potential. From a 50,000-pound thrust demonstrator, the concept grew to 250,000 pounds in just a few years. In June of 1964, the FAA awarded both Pratt Whitney and General Electric contracts to develop an engine for a proposed supersonic transport. With the experience of the J58, Pratt & Whitney's designers appeared to have a substantial edge in development of this 54,000-pound thrust high-Mach power plant, and they tackled the project with enthusiasm. Employment rose to 7,000. The engine was completed ahead of schedule and ran on March 31, 1966. By December, the test phase was complete, and the engine had run at speeds up to Mach 2.7 at 65,000 feet. The Christmas holidays began on a jubilant note. On New Year's Eve, that euphoria was shattered with the announcement that GE had won the SST engine contract.
The unfortunate thing is that even though the SST program didn't proceed, GE had millions of dollars in development for high-temperature jets that we didn't get.
Other development programs, such as the C-Jet marine engine, were lacking in a viable market. In an effort to keep the facility alive, responsibility for all J58 overhaul was transferred from East Hartford to FRDC, with production and assembly of several other military engine components. In September 1967, FRDC received a contract for development of the ST-9, a new turboshaft engine for the proposed U.S. Army UTAS helicopter. The company also started contract work on a 250,000-pound thrust rocket engine and began research on the use of gas dynamic lasers as weapons systems. But none of these programs offered the immediate business benefits the company required. The future of FRDC was still in jeopardy. 1967 was a rough year for the Air Force, too. Soviets introduced the MiG-25, a formidable new fighter which shattered numerous performance records and threatened NATO air dominance. In the skies over North Vietnam, it was increasingly evident that the dogfighting capability of current U.S. fighters was marginal at best. The Air Force quickly initiated a competition for a new air superiority fighter, the FX competition. The Navy, too, was seeking a new engine for its proposed F-14. Once again, Pratt Whitney was pitted against GE. This was a must-win situation, and FRDC responded admirably. Their entry? The remarkable F-100. 1968, FRDC's 10th anniversary. 10 long years. 1 short decade. America was now deeply enmeshed in Vietnam, but results seemed frustratingly elusive. World War II had ended with a dearly bought but unequivocal victory. Korea concluded with an unsatisfactory and unsettling stalemate. With Vietnam, the public became increasingly skeptical of official reassurances. Government news releases reported a light at the end of the tunnel, but the massive communist Tet Offensive of 1968 finally shattered public complacency and polarized the nation. Ahead, the nation faced a painful extrication from Southeast Asia. There were moments of glory, though. In 1969, we watched our TVs in awe and anticipation as Neil Armstrong took that first small step and forever changed mankind's place in the universe. Our old icon, the automobile, no longer sported fins, but cars were still aerodynamic and powerful. If the events of the late 60s and early 70s left the public disillusioned with the military-industrial complex, Pratt & Whitney knew the future was not that simple. Regardless of public opinion, the nation still faced very real threats and possibilities. The F-100 competition was challenging. The Air Force demanded an engine with a higher thrust-to-weight ratio than any previously designed. Winning the contract was critical to FRDC's survival.
Well, the biggest problem in the F-100 is to get the weight down. The original design we had didn't make it. We had some pretty good information that told us we were off the mark on the weight. And Bill Brown, I will call credit for getting a design change that got the weight down. But doing this is getting the weight down is what made it risky. The other parameters were well within hand. Trying to do this job with the weight that we went after was a real tough program. And to do this, we did need to have IN 100 in the turbine discs.
Another materials laboratory breakthrough, gatorizing, provided one key to solving the weight problem.
We did a very unusual thing. And frankly, I don't remember why we did it, but we did. We took the material and we did not heat treat it, and we tested it. And we tested tensile properties up in the 1700 to 2200 degree range, and stress rupture and tensile. And we were absolutely amazed when the rupture results came in, because as soon as the guy loaded the specimen, it just stretched like chewing gum. And we became very excited over this, because these alloys like IN 100 are very difficult to move, to forge without cracking and so on. And here was this stuff just, stretching like putty. So it occurred to us, gee, if you can get the material in that kind of condition, if you can pull it like that in tensile, why can't you put it into compression, which is a forge motion, and do the same thing and come out with forgings that are very, very close to that shape, with a reduction of machining and something that had no cracks in it. Like I said, I have a super strong alloy like IN 100. So we set up a little forging rig, put the material in a superplastic condition, heated up the whole system, and held it at temperature. And we were able to make little small pancakes with different beautiful surfaces. And type configurations. So that said to us, boy, we got something here. And we went after a big Ford cycle, and then, of course, we sold it to the Air Force for F-100 disc. And in fact, we sold it to them, and we won the contract before we ever made full-scale disc. We based everything on small-scale pieces, which is kind of dangerous.
Dangerous it may have been, but the full-scale IN-100 discs proved every bit as good as the tests promised. The result was a lightweight engine with an 8-to-1 thrust-to-weight ratio, producing nearly 25,000 pounds of thrust. It was a 25% improvement over any previous engine. The first F-100 engine ran June 30th, 1969, and began a grueling test series. Problems encountered were quickly fixed, and the schedule was maintained. In March of 1970, the Air Force announced Pratt Whitney's selection to power the new F-15 Eagle. Simultaneously, the U.S. Navy selected a version of the same engine, the F-401, for the new F-14 Tomcat. Full-scale development began immediately. It was a rigorous schedule, running in parallel with airframe development. In November 1974, the first production F-15s were delivered on time to the U.S. Air Force. The Navy version of the engine, however, experienced delays. The Navy canceled its order for the F-401 and opted for East Hartford's existing TF-30. In May 1970, NASA requested design proposals from Pratt & Whitney, Rocketdyne, and Aerojet. A high-pressure, reusable, hydrogen-oxygen-powered main engine for the future space shuttle.
Dick Mulready, along with some folks from the research lab, had started a program of high-pressure, high-chamber pressure rocketry, and had demonstrated very successfully that a very high-pressure engine could be built and cooled and would be very efficient. So when the Space Shuttle main engine program came along and the request for quotation went out for the engine, we responded with a proposal based on that technology. The company had put about 10 years of effort into it and a lot of company money. It was R&D, of course, but it was still all paid for by the company, and we had actually demonstrated the concept at full price. So we submitted our proposal to NASA, and in this new environment that we were learning to live in, where a contractor is just a person that NASA uses when it's convenient for them, they gave our design, our proposal, of course, which we had written under their aegis and they had paid for, they gave that information to our competition. And they said, we like this design concept, this high-pressure engine concept, better than the concepts which you have put forward. So we want you, the competitors to Pratt & Whitney, to take their concept and make a proposal based on that. Well, that was an insult beyond insult as far as we were concerned. But it happened, and we had to live with it.
Despite this turn of events, Pratt & Whitney was confident that their experience and established technical expertise would prevail. It came as a tremendous shock when the contract was awarded to Rocketdyne in July 1971. A satisfactory explanation for the choice was never offered. Pratt & Whitney appealed the decision to the U.S. Comptroller General. After a 6-month legal battle, Pratt & Whitney lost the appeal. The decision effectively took FRDC out of the space business for years to come, except for continuing development of the workhorse RL-10. That loss, however, may have had some positive aspects.
My view is it's a doggone good thing we didn't get that competition because we were right in the middle of the F-100 program at that time. And there was absolutely no way in the world that we could have handled the two of them. They both would have failed, and we would have gone down the tubes.
In December of the same year, the U.S. Army selected GE's entry over Pratt & Whitney's ST-9 to power its new utility helicopter. On the plus side, however, in addition to the huge new F-100 contract, FRDC's laser research was generating interest. In December 1972, the Air Force funded a program to place a gas dynamic laser aboard a flying test bed, the Airborne Laser Laboratory. One key architect of Pratt Whitney's laser program was William Missimer.
Actually, after we lost the engine contract for the Space Shuttle main engine to Rocketdyne, it was a big blow to the company, but we had developed facilities and capabilities in the area that fit the type of laser that was in vogue at that time very well. It was a gas dynamic laser, which, believe it or not, from a propulsion standpoint, is almost like a rocket engine. It's had some cryogenic fluids and had very tight tolerances. And the only thing that was new to us and foreign was the optics part. One of my first jobs was setting up the optics for some of these tests. And I remember we had the Army in one day, and they set up their experiment downrange. I think it was a tank or a piece of a tank or something. And we had set up the telescope, and there was a wind blowing quite a bit. We all went up to the control room, closed up, buttoned up the facility the same way you would for a rocket test. It's all remote controlled. And the Army guys were sitting there, and we pressed the button, and the laser came on, and the beam didn't appear for a while downrange. And then all of a sudden it was there, and it did its thing. We couldn't figure out what the delay was. So I went down in here, the wind had blown the door shut, the steel door shut on the telescope room, and that Hummer burned a hole through the door and then went downrange and did its job. Well, after we did the initial research work on what was then called the XLD-1, that was a 1 megawatt boilerplate laser that we put into E8 stand, and proved the capability of the high energy lasers, the Air Force got very interested in a lightweight version of that would go into a modified 707 airplane. But then the challenge became, how do you lightweight this thing so it's flyable and also make it safe? Now, here's where the jet engine smarts came in, because they looked at Pratt as being able to man-rate something from a safety standpoint, which was extremely important. They could not, or we could not, afford any kind of an accident in flight with this demonstrator, even though it was a highly classified program. So we won the contract, and in those days, it was a pretty sizable contract to make this a flyable, lightweight system.
In 1973, General Dynamics chose the F-100 engine for the YF-16, its entry in the Air Combat Fighter competition. The YF-16 won the competition in early 1975, and Pratt & Whitney's F-100 was a key part of its success. That same year, the F-100 further proved its quality when the F-15 Streak Eagle set 8 time-to-climb records. In its final flight, the Streak Eagle accelerated from a dead standstill on the runway at 98,424 feet, 19 miles straight up in less than 3.5 minutes. This smashed the MiG-25's old record by nearly 30 seconds. 4 NATO countries, Norway, Denmark, the Netherlands, and Belgium, had recently formed a consortium to seek a new fighter. The performance and cost of the new F-16 and its F-100 engine caught their eye. As an incentive, Pratt & Whitney and General Dynamics offered an unprecedented international co-production agreement, and the F-16 was quickly flying with and being co-produced by our allies. Now, with East Hartford's TF-30 and FRDC's F-100, Pratt & Whitney held the enviable position of powering the 3 best fighters in the free world: the F-14 Tomcat, the F-15 Eagle, and the F-16 Fighting Falcon. To meet the demands of the F-100 program, FRDC had grown further, and in 1976, as part of a major reorganization, it was renamed Pratt & Whitney Government Products Division. The new division was given management responsibility for all military engine programs, including the J52, J57, J75, TF-30, and others. By 1978, our 20th anniversary, things had changed dramatically for the company and the nation. The fuel crisis of the 70s affected our economy, and our psyche. Our cars reflected that change. The great land yachts and gas-guzzling muscle cars of the 60s were giving way to smaller, more fuel-efficient cars, many more of them with foreign names. 4 years earlier, after more than a decade of fighting, the Vietnam War had reached a dismal end. Public sentiment was now strongly against military spending and military involvement. Interest rates were rising. The country was slipping into recession. It profoundly affected the way consumers made their purchases. Pratt Whitney's biggest consumer, the U.S. government, was no exception. Pratt & Whitney had been riding high on the new F-100 contracts, had slowly lost touch with the customer's needs, and was in for a shock. Frank McAbee had just become president of GPD.
Traditionally, when you won a military engine contract, you had that business and your business base that you could forecast, and you knew you were going to have the production volume in future years to support you. That particular tradition was about to change, though, and was changing very rapidly in the early 80s. When I became president of GPD, it had almost reached the boiling point. Those of us who worked in Washington were well aware of the fact that the F-100, which had just been introduced into service, while it was performing beautifully, was having some problems. We knew that the military was not particularly happy to have those problems, which the opponents to the military program in the Congress could use as an example of how the military really didn't know how to run a program and that everything they did turned out bad. So the pressure was on both sides. We knew that the military was seriously considering giving some of our business to GE. We knew that GE had developed their F-110 engine in competition with the F-100 earlier on, and that they had continued to develop it to some degree with their own company money to have in case our engine didn't work out. And they pursued a very active and vigorous lobbying campaign with both the Congress and the military to displace us, to show that our problems were bigger than we were able to handle. Any issues that arose where there was any type of question as to Pratt & Whitney's responsiveness to the government's problems or to the military's problems, competition obviously took advantage of that and played that up. So it was a very tense time. And the engine was working fine. It was actually working too well because it had such a high thrust-to-weight ratio, so much better than any previous engine, that the pilots and the operating units were flying the airplane well outside the envelope. They never wanted to pull the throttle back. They wanted to use the afterburner a lot. And you know how pilots are. They're like the rest of us. They like sports cars, and they want to zoom around the sky. But as a result of that, the engine was being pushed beyond some of its design limits, and it was having some premature failure. So we had that to contend with. The Air Force, in the meantime, had decided that the way to get our attention, perhaps, to threaten to give part of the business to GE. Our management did not respond well to that. We just didn't understand, and I'm sure that it wasn't unusual that anyone would have understood that particular circumstance, that we had won the competition. It was our engine. We would fix the problem. So why not just leave us where we were? Leave us alone. Let us do the job. Just give us money and go away, which is not all that different than the Pratt attitude over the years. In any event, the Air Force decided they were going to run a competition, and thus began the Great Engine War, as it's known. It was Pratt against GE, and the proposal that we submitted was based on, to a great degree, us getting all the business, and that really wasn't what the customer wanted, and as a result, GE was given 65% of the contract of the first year. That was a great disappointment. It was a tremendous shock to us, to everybody in the plan, everybody. A lot of gloom and doom.
The Great Engine War, as it came to be known, had a profound influence on every aspect of GPD's existence. Winning back the customer's confidence was not an easy task. It required a drastic change in corporate culture. Quality, customer support, and cost were critically examined and constantly emphasized at every level of business. The company even tried to change their image with a modernized version of the logo. Employees were less than happy. To counter the antipathy that had evolved, Pratt Whitney began sending engineers and designers to air bases to see their products in real-life operation. Air Force and Navy aircraft were brought to the Florida facility so employees could see the end results of their labors and meet the men who flew them.
I remember the first time we had an F-14 come into GPD. The pilot of that airplane was named Hank Kleeman, Commander Hank Kleeman. He had been the pilot who shot down a Syrian jet about 6 months or a year prior to the time that he visited the plant here. He was a hero. He came here with his radar officer, the other member of the crew. They landed at Gwynn, and we towed the airplane up in front of the plant, and then the two pilots went around and talked to people. And I'll never forget, there was a lady who worked in plant engineering. Not a very high position, but nonetheless a good employee. And she broke into tears while she was talking to Hank Kleeman. She was so proud of the part that she had played, that Pratt Whitney had played, and that victory that Kleeman was part of, that she actually broke down and cried. And to me, that was a tremendous insight into the value of having people feel part of what you're doing.
Eventually, the company proved their new demeanor was real, and the traditional logo was restored. This process of soul-searching, of analysis of attitudes, reached beyond the customer. At this point, Bill Missimer was executive vice president.
When Harry Gray came to UTC, before that was actually United Aircraft, he brought with him the many new ideas, one of which was to make profit centers, and that's when we became Government Products Division. And another one was he had a code. He said that we have a responsibility to customers, shareholders, employees, and the community. Bill Dwyer was an exceptionally fine individual who fit his role as vice president for community relations extremely well. And he was a very humorous guy. He always had an appropriate joke. He was an outstanding speaker, and you could tell that he loved people. He got us involved with, obviously, United Way. He was involved with the Urban League, Special Olympics. Some of his legacies today, the science fair, for example, that the engineers do such a good job of encouraging, are all legacies of Bill Dwyer. He was very well thought of in the community, and as you know, there's now a senior high school named in his honor, not too far from here.
Through the late 70s and the 80s, improvements continued on the F-100, and it grew into a family of engines. The PW200 model featured performance and durability improvements. In part, these improvements came from new materials laboratory innovations, like RSR and Gator Guard, an improved plasma spray coating system that found many uses. RSR was an innovative method for processing inert powdered metal alloys. Bill Moore explains.
RSR stands for Rapid Solidification Rate, and you make powder under inert conditions. We invented a machine, our boys came up with a fantastic machine for making powder and rapidly solidifying it. What happened was it consisted of a spinning disc, and the metal would be poured in a vacuum chamber from the crucible into a nozzle onto a spinning disc. And the rotation of the disc centrifugal force throws the metal out in 360 degrees all around. And then we had a blast of argon, or circular curtain, around the spinning disc in order to increase the speed of solidification. And what we were doing was, as we had always done since the J58 development, we were reaching for a stronger turbine blade material using the RSR.
East Hartford's materials laboratory created another breakthrough technique: single crystal turbine blades. This innovation was quickly adapted for use in military engines and dramatically increased the hot section life of the F-100. The development of single crystal blades, coupled with a new digital electronic engine control, the DEC, ushered in the F-100 PW220. The PW220 set a new standard for durability, reliability, and safety. Work also continued on a higher thrust version of the F-100. With almost 5,000 pounds more thrust, PW229 entered operational service in the F-15E and the F-16C by the end of the decade. A 20,000-pound thrust straight turbojet version of the F-100, the PW1120, was not so lucky. It was selected to power Israel's Lavi fighter, but that program died in the Israeli Knesset. Two other programs of the 80s did not fare well either. GPD developed the PW3005 for the V-22 Osprey, the T-800 for the Army's LHX helicopter. Both these turboshaft engines lost their competitions. During this decade, the Navy began re-engining F-14s with GE's F-110, and production finally ended for the venerable J-52 used in the A-6 Intruder and EA-6B Prowler. For the first time since Pratt Whitney's founding, the company was no longer building engines for the U.S. Navy. NASA was now seeking improved turbopumps for the Space Shuttle main engine. Current Rocketdyne pumps had to be rebuilt after each flight. John Balaguer was the division executive vice president at the time.
And liftoff.
There became an opportunity, which was called the alternate turbopump program for the Rocketdyne engine with power separation. And we went after that tooth and nail. That was the program that we felt we had to win in order to start our space program growth that we so desperately needed. And we worked very hard on that. We brought in a lot of people who were very knowledgeable in the industry, people who had retired, people who were out of NASA and retired, to put together one of the best proposals I think I've seen. We won.
Pratt & Whitney resumed work on their SSME pumps and was now able to offer NASA turbopumps that could fly 55 missions between overhauls. But much development work still lay ahead. The RL-10 was continually evolving too, and an unparalleled success record. Over 500 successful firings in space.
We have two Centaur engines up and running.
Space provided another outlet for the company's technical excellence and creativity. NASA tapped Pratt & Whitney to develop an engine for the proposed National Aerospace Plane. NASP stretched the boundaries of conventional engine design. The aircraft was designed to take off and land like a conventional airliner at existing airports, but would fly to the very edge of space at speeds of Mach 25. It called for an engine of unprecedented versatility, one that would start as a conventional turbojet, convert to a ramjet, and ultimately to a true rocket engine. Pratt & Whitney had one of the country's few Cray supercomputers. Design work that would have taken years was condensed into months. New materials and concepts were explored. Subscale testing was already underway when congressional budget cuts put the program on hold. The nature of air warfare was evolving in the early 80s, and agility was becoming an increasingly important issue. Research began on vectoring nozzles for jet engines. Roger Bursey was in charge of this program.
Well, there was a lot of discussions back in the 60s by a German aerodynamicist, Dr. Wolfgang Herbst. He felt that the new aircraft of the future had to have a lot of agility. And in the upper left-hand corner where there's a minimum
of aerodynamic power. He felt that some maneuvers would enhance the agility of aircraft in that what was known as the post-stall region of the flight envelope. And he felt that one of the means of achieving this agility was to have the use of the thrusts of the engines to augment the aerodynamic surfaces. In order to accomplish that, it could have been done with a series of external paddles that could deflect the thrust. However, that was cumbersome, added weight, added drag. Hence, the aerodynamicists of that era determined that if we could come up with a system to vector the thrust of the engine and have it transparent to the pilot, we could accomplish those feats. With that in mind, our advanced technology team here started a series of testing with scale models, and then eventually led to a very successful flight test. And I can recall the first flight. It was absolutely rewarding on May 10th, 1989, out at Edwards Air Force Base to see the two-dimensional nozzle fly. The folks indicated that if now we had the success of taking thrust vectoring into the pitch mode, and they says, if we can do this, why can't we do this? And that's called the yaw mode. Coupled with the pitch and the yaw, we says, if you can do both, why can't you have a multi-axis thrust vectoring? So we launched a review in 1992 with a ground demonstrator made up of various components and successfully demonstrated the multi-axis thrust vectoring.
The Air Force's changing mission meant quicker response time on a global scale. And the current generation of airlifters was not versatile enough to meet the new demands. Design work began on the C-17, an aircraft capable of moving huge loads anywhere in the world and landing on short, unimproved strips practically at the front lines. Pratt Whitney developed a militarized version of the proven PW-2037, the F-117. It provided the power, durability, and reversing capability needed by the Globemaster III. By the end of the 80s, the F-100 and the F-15 would have seen 15 years of service. By the new millennium, it would be over a quarter-century old, ancient by fighter aircraft standards. Quietly in the background, work was underway on a superb new fighter engine, the next generation beyond the F-100. Guiding this effort was Frank Gillette.
We built this engine on the information that we got out of the ATAG program, which is Advanced Technology Engine Gas Generator. At our plant, we call it 689. The compressor, the combustor, and turbine were designed before 83 that we just picked up and just refined so that we had a real good common core, which gave us a basis to do everything. Our design objectives at that time was a balanced design. We wanted cost, we wanted durability, and of the most important we wanted to do this time that hadn't been done is increase our supportability. The performance, we wanted the highest specific thrust engine that has ever been made. We ran our first demo engine in October of 1986, and it was a thrill to see this very powerful engine run down in the test stand with a 2D CD nozzle. It was very exciting for us, and we were very proud of all the work and accomplishments of our people.
The PW-5000 was well underway when the government announced a competition for an advanced tactical fighter to replace the aging F-15 in the next century. Two aircraft company teams, led by Northrop and Lockheed, would compete along with two engine manufacturers. Each engine would fly in both aircraft. It was Pratt & Whitney versus General Electric again. The PW-5000 officially became the YF-119, and design and testing shifted into high gear.
The airplane wanted supersonic persistence. And that means an airplane can go faster than Mach 1 without using the afterburner. And that was the exciting thing. That's the big change in technology that the ATF would have over any other airplane. In other words, the ATF, or now the F-22, can fly the same place that an F-15 can go without using the afterburner. The other big change to this airplane is low observables, which means a stealthy airplane. And we've accomplished that over a lot of technology and a lot of luck. This will be an awesome airplane. This airplane will be as good as an F-117 stealth fighter, but it'll go supersonic and it'll turn and burn, and it'll put an air dominance into this United States that we will always have superiority. We won't need to talk about superiority, we'll talk about air dominance.
1988, our 30th year in Florida. The facility was now called Pratt Whitney Government Engine Business. With the advent of détente, the old Soviet peril that had driven so many of our enterprises was rapidly diminishing and would soon vanish.
The aerospace industry had a saying, and it was that we've lost our army. It required that we do some major restructuring of the company, and we did. Unfortunately, we were not unique. We ended up in our restructuring program, which at that time was not called a restructuring program, but today it's a household word. We lost about a third of our business, and we lost about a third of our resources. Most of that was people. I think we handled those restructuring actions in probably the best humane way we could. We spent a lot of time making sure that the hurt to people was minimized, and it still hurt. At least we knew we had done the best job we could to minimize that and to try to keep families whole and move on. So it was a tough time for Pratt & Whitney, especially tough for the military side of the business. And the Air Force picture, the U.S. Air Force picture, was not pretty, which was our #1 customer. So we really focused on international sales, which were really probably the savior and a large part of the F-100 program. We did very well in the international campaigns. Not that we won them without some difficulty and some financial contribution, but we did do very, very well as a team. And we're able to bring in additional volume to put in on top of the U.S. Air Force domestic volume. At the same time, we wanted to be sure that we didn't lose sight of the ultimate goal, which we've been working on for many years. Under the leadership of people like Frank Gillette and Gary Plord, we're working the next engine, the next advanced engine, for what that program was called at that time was the Advanced Tactical Fighter.
Contrary to public euphoria, the end of the Cold War revealed a world more unstable and full of unconfined threats. A nation was reawakening to its resolve as a world leader. Pratt & Whitney's Florida facility had responded to the challenges of the previous decade. The spirit of teamwork that exemplified the early days of FRDC was reborn. New prizes were there for the company to win, if they proved worthy. In 1990, as Pratt & Whitney accelerated their pursuit of space business, United Technologies formed Space Propulsion and Systems, uniting its Chemical Systems Division and United Space Boosters Industries with Pratt & Whitney's space business. Doug North became its president. As the decade closed, ATF flight competition was underway, and problems that emerged were corrected, often with the help of the advanced computing power now available, but also by the instincts of good people.
Well, my closest moment, I'll have to say, during the 15 years of being engineering manager of the 119, was an engine called YF4. It was the first engine that went into supposed to go into the YF-22. We had run the engine down here to pass our qualifications to ship it to Edward. Then the engine passed the qualification. This was on a Thursday, and the C-141 was supposed to come in on Tuesday of the next week. So we had a lot of work to do to get ready, packed to go out. And obviously, GE was already flying in the YF-22, and we had to fly to be a winner. This guy came up and still kept telling me the engine wasn't right. On Friday, we decided to take the engine apart, and I know a lot of people didn't agree with that, but these two guys really instilled in me we should do it. We took the engine apart, and we found out that on the #2 bearing support, we had left all the bolts out, and the only thing that was holding this engine was the snaps. So we saw that on Saturday morning. Thank goodness with the the persistence of these people. We put those bolts in, passed the test, packed that engine up on Saturday night, had it ready Monday. The plane came in on Tuesday. We flew it out to Edwards, and that engine was the first one to go fly with engine number 5 in YF-22. So the lesson I learned is listen to your people. Without that, this engine on the first roll-up probably would have come out the inlet. We could have lost the contract. We could have not been here in Florida enjoying the great reputation we have. So what I learned out of that is listen to the workers. When they've got a gut feeling and data that says to change it, please listen and change it. Probably the most exciting times in my life is to go out and see the YF fly for the first time. Very emotional. Brings tears to your eyes. I have trouble talking about it right now. And then we flew the YF-22, and that was really thrilling.
Finally, on April 6, 1991, came the announcement we had waited for. Lockheed's F-22 would be the new air dominance fighter for the 21st century, and Pratt & Whitney's F-119 would give it the needed muscle.
We won the honor to power the ocean.
PYBBN vectoring nozzles were undergoing flight evaluation on the F-15 Active and would soon be installed on the F-16 Vista, setting the stage for a new generation of thrust vectoring engines and aircraft. The SSME turbopumps also progressed through critical testing here and at NASA facilities. Finally, on July 13, 1996, a single Pratt & Whitney alternate SSME oxidizer turbopump flew aboard the Space Shuttle.
And liftoff of Space Shuttle Discovery to complete NASA's constellation of tracking stations in the sky.
By year's end, another shuttle flight carried Pratt & Whitney pumps on all 3 main engines. Work was also well underway to certify the fuel turbopumps. The space business was growing. There was potential to help make up for decreased military spending, but it required a radical business approach.
We felt that we were lacking in having no resources dedicated to large liquid boosters, which were, from everything we could see, the booster of the future. There was no money to develop one in the United States. NASA didn't have the money. We certainly couldn't fund a program to develop a new booster engine. It was just too expensive. We examined the Russian stable of technology and engines they had, and we found that there was an excellent engine put out by Energomash, a company just outside of Moscow. And that engine led to developing a 2-barrel version of that 4-barrel RD-170, which was called the RD-180.
Pratt & Whitney entered into a joint venture with Russia's NPO Energomash to adapt and market Russian RD-120 and RD-180 rocket engines. It was a high-risk gamble, considering the unsettled nature of Russia's new politics. But NPO Energomash is the acknowledged world leader in heavy-lift liquid-fuel rocket engines. The RD-120 arrived at the Florida facility, was mounted in the E-8 test stand, and on October 11, 1995, became the first Russian rocket engine ever fired in the U.S.
Start. 1, 2, 3.
The much larger RD-180 produces nearly 1 million pounds of thrust and has already been selected for the Atlas 2AR and 3A launch vehicles. The RD-180 has also been selected to power the new EELV, the Evolved Expendable Launch Vehicle. Now, with nearly 600 successful firings. Since its inception, Pratt & Whitney's space propulsion efforts existed to serve government customers and operated in conjunction with the jet engine side of the business. Now, with a renewed commitment to space propulsion, a broader base of products, and a rapidly growing commercial market, the company created a new business unit, Pratt & Whitney Liquid Space Propulsion. Angie Negron is the Vice President and General Manager of LSP.
We have been very active in hypersonics. We have 2 active programs, demonstrator programs, one of them for the Air Force Research Lab, and a derivative of that program is called the ARMED program. Both of those use kerosene fuel and are storable. And again, they really are opportunities that we see to grow this business. The RL-10 has been around for 40 years. And the idea of replacing the RL-10 is somewhat sad, but also, I think, sends a real message that Pratt & Whitney is serious about the space business. I've gotten tentative approval, and it has to go to the board, to build an engine that we call CCAWS, Commercial Cryogenic Advanced Upper Stage Engine. I think we have the most determined people that I have ever worked with. And as a result of that, they are continuously beating at my door to talk to me about new things and new ways that we can grow this business. You know, they've seen the potential, they've had the vision, and they've just been waiting for the company to catch up.
Even after nearly a quarter century, the venerable F-100 was still evolving. PW-229A adapts F-119 fan technology for a thrust increase up to 34,000 pounds, 10,000 pounds more than the original F-100 of 1974. It offers improved maintainability and is a strong contender in Pratt & Whitney's growing overseas marketing effort. And while all of this was going on, derivatives of the formidable F-119 were selected to power both contenders in the new Joint Strike Fighter competition for the U.S. Air Force, the U.S. Navy, the U.S. Marine Corps, and the British Royal Navy. After more than 20 years, Pratt & Whitney would be producing a new engine for the Navy. The first production F-22 was unveiled at Lockheed Martin's Marietta, Georgia plant on April 9, 1997.
Today, we are pleased to officially name the F-22 after a special class of fierce and proud winged warriors. Today, we name the F-22 the Raptor.
What you are building, if you build it right, if you dedicate yourself to perfection, will allow people across the planet to be free for the next half century, will allow America to lead the world for the next half century. And someday down the road, because of your dedication and your hard work, the pilot is going to return safe, who might otherwise have died. What you are doing is patriotism at its most important and at its best. And on behalf of that pilot and their spouse and their children, I want to thank each and every worker everywhere across this country who are helping America remain the leader of freedom.
On September 7, 1997, we witnessed the flawless first flight of Raptor 01.
Okay, control, I'm ready for engine start. You're clear left engine start. Pick up the throttle leg. Right. Throttle is in idle. Rotation. 10%. Light off at 22. Okay, canopy's coming down. Dobbins ground, Raptor 22, flight of 3, F-22 from spot 53 on the south side. Raptor 06 and 19, the F-16s from the guard ramp. Taxi. Am I cleared to go? You are clear. Power's coming up. Release brakes now. Everything looks good. A little fast on the climb. Coming back. Baby gets right on up here. Feels real good, PA. Good ride. Yep, great ride. Tower Raptor 22 is rolling out at 3.6 miles.
Raptor 22, you clear to land, wind 140 at 4.
And now, 1998. 40 years, 4 decades, a full generation and more of engineers, designers, assemblers. It was a year marked by yet another landmark event, the first 2 JSF-119 engines to test in an unprecedented time, a mere 18 months after the contract award. This was also the first time in history that 2 different new Pratt Whitney engines went to test at the same time. Together, the F-119, the Lockheed JSF-119, and the Boeing JSF-119 represent the evolution of a new dynasty, a new family of engines in the tradition of the Wasp and the F-100. 1998. The Florida facility is now called Pratt & Whitney Large Military Engines. Division President Ansel Tukes shares his vision of the future.
Being assigned to Pratt, Florida was certainly a joy to me. When I came to Florida, I found a wonderful place, a place that my predecessors and all the people that have worked here for many years had built a very fine business. So first of all, I came into a very nice situation. We have a wonderful market position on our military business here, built on a long tradition of strong technology. I can't think of a better place to be in the aerospace industry than at Pratt & Whitney, and particularly on the government side of the business. So we're in the front line of the fighters for the U.S. Air Force. We have a majority of wins around the world for application of the F-100 engine in both F-15s and F-16s. We have the 119 engine, which is a foundation of power for the F-22 and for the Joint Strike Fighter. Our tradition here, based on gas turbine technology, is just as important on the space side. As you well know, our liquid space operations are centered here, and Angie Negron is doing a fantastic job leading that business and developing markets and technology. I think one of the most important parts of our success is the way we relate to one another. And Pratt & Whitney here in West Palm Beach, our Florida operations are truly a family. And that's why it's easy for us to build strong development teams. Our IPD process is based on communicating between people, and we certainly have a spirit of core that I believe is key to our success in the past, today, and for the future.
40 years.
I kind of divided into 4 chapters, if you will, from a culture. The 60s were highly exciting, experimental work, more challenges than you could possibly imagine. Technically, how to get things done, we were pushing the frontiers in everything. Extremely exciting. Our program, the J58, the RL-10, all the way down through the trenches, everybody was turned on. So that's the 60s. The 70s, I would put in, 2 things happened. One, we won the big one. All of a sudden, man, we have the F-100 program, and we've got to produce, because our engine is in every leading fighter in the United States. The supremacy of the skies rests on, from a propulsion standpoint, rests on these kids. We got to make it happen. So I would say the 70s was the make or break us as a division. Became a division in 1976. And we did it, not without a lot of trouble, not without a lot of setback. I always felt that place out there performed best under pressure. Now, I know all the program management theories that you shouldn't ever get into that situation. Well, that's the way the world is, you do. But I've never seen a team produce under pressure the way that bunch did. On the F-100, on the F-119 later, you could see it. We were at our best under those circumstances. So that was the 70s. The 80s, the great engine war. All of a sudden, we brought this lion into the tent, and in the eyes of our customer, our tent was too small. And so he decided, and it's his right to do so, we should have an engine competition. But the 80s was the great engine war, which consumed us too. And then for now, the 90s is the 119 and the legacy that will give as we move into the fighters of the future. Thank God we're in the two that are on the boards now, the F-22 and the JSF. So our challenge, our legacy, if you will, is how to win the next.
$40
I wish I was starting all over because it's, I think it's rewarding to see technology that the jet era, which is about 50 years old now, in my opinion, is only about halfway through its life.
And all the things that we did and accomplished were due to one thing, our people. Sounds corny, but it's true. Without them, we'd had nothing.
42 years have been very quick, and it seemed like just yesterday I started. If I had to do it all over again, I wouldn't change a thing.
It was a very happy time. It was a time when people loved to come to work. They were so devoted to making this equipment work. They would spend all kinds of extra hours at it. And it's hard to explain. People felt so everybody was just very happy with the job.
And then to win, when John Balaguer said in April of 1991, April 23rd, that nail stick and infamy, that we had won. The ATF program was very exciting. Everybody was in tears, hugging each other and having a great time. And then when we saw the final airplane, which is our production model, fly just last year out of Marietta, we were all thrilled and proud. And everybody at Pratt Whitney has the right to be proud of doing a great job and making our country have air dominance for all our grandkids in the future.
Well, the world has changed irrevocably in these 4 decades. Some things seem strangely familiar. Again, we held our breath as a national hero, 77-year-old John Glenn, blasted into space. This time, aboard the Pratt & Whitney-powered space shuttle. Pratt & Whitney's Florida facility is perhaps a little less remote now. But the challenges are as exciting, as demanding as they were 40 years ago. And the promises for the future are even more inspiring. This fighter pilots call it the sound of freedom. It echoes all we have been, all we are, and all we will be. It's the sound of pride, hope, and glory. 40 years, that thunder in the sun has been our daily declaration of triumph.
The P-51 Mustang, the most dominant escort fighter of World War II. It helped blaze a trail from England all the way to Berlin for America's bomber force.
Of course, the Mustang was a revelation. It was the war winner.
Its creation was sparked by a mixture of genius and chance. The Mustang and its 2-stage, 2-speed supercharged Merlin engine were the end result of years of technological development. From World War I to World War II, each generation of aircraft went ever higher and faster. But the Mustang's marriage with the Merlin might never have happened. National pride delayed the coupling of these two great innovations. But a new deadly German adversary changed everything.
The Focke-Wulf 190, this was really a top-notch fighter aircraft.
With the FW-190 terrorizing the skies of Europe, the British and American forces swallowed their pride and joined together to create the ultimate fighting machine. December 17, 1903. The Wright brothers' aircraft, the Wright 1, successfully takes off, initiating the dawn of aviation. Man had already taken to the skies with gliders and balloons, but this was the first time that an engine had propelled him into the air. The Wright 1's engine was a crude design by today's standards and put out 12 horsepower only. It was an inline engine, meaning that its cylinders, 4 in total, were mounted in a straight line, a layout that would inspire some of the most advanced piston-engined aircraft ever created. Though a simple design, the Wright engine was innovative. It was the first engine to make use of a lightweight cast aluminum crankcase. Every pound counted. With a heavier engine, the Wrights may not have made history that winter's day in North Carolina. Aircraft weight and power would continue to be important to the evolution of flight. World War I was approaching, and the newly formed air forces of the world needed reliable engines with enough power to sustain flight during operations. From France would come a new type of power plant to take the fight into the air, the rotary engine. Rotary engines operated differently than the inline ones used by the Wright brothers. The cylinders were arranged in a radial pattern rather than a line. When the engine was fired up, the crankshaft remained stationary, while the crankcase and cylinders rotated around it. A rotary engine had one giant advantage over the inlines of the era. It was much lighter, and thus gave a pilot better performance during combat or while trying to evade an enemy. However, the rotary engine was not without its shortcomings. It had poor fuel economy, as it was often run on full throttle. It also provided an unpleasant ride. Castor oil was mixed with the fuel mixture for lubrication, with the side effect of heavy fumes, smoke, and an oil shower for pilots. Turns with a rotary-powered aircraft could prove treacherous. As the whole engine rotated, it produced a gyroscopic effect. A turn to the right, at full power and low level, could end with the death of a pilot. Rotary-powered aircraft remained part of Air Force inventories till war's end, but they were gradually supplanted by the inline engine. Inlines based on the same principles as the one found in the original Wright plane kept improving in terms of power and performance. Between the wars and across the Atlantic, a new type of aircraft engine would emerge to dominate American aviation. The U.S. Navy was looking for aircraft to populate its fledgling aircraft carriers. Space on board was extremely limited, but aircraft with inline engines often had lengthy noses. Their engines, built with rows of cylinders, took up too much space on cramped carriers. Rotary engines, though more compact, had too many other weaknesses to be serious contenders for the role. There was, however, a third type of engine. Before the war, there had been limited experimentation with radial engines. At first glance, these appeared to be just like rotary engines. It's only when they are fired up that the difference becomes clear. In a rotary engine, the crankcase and cylinders rotate around the crankshaft. But with a radial engine, the crankshaft rotates while the engine block is static. Radials often weren't as powerful as inline engines, but they were less complicated. They were cooled by air rushing over the engine rather than through a liquid cooling system. This made radials less vulnerable to battle damage, which might rupture the coolant lines. Navy pilots who might have to travel long distances over the ocean to get to a target needed an engine that would be sure to get them home under any circumstance. Most importantly for the Navy, radials were smaller than inline engines, so a greater number of aircraft equipped with them could be stored on board their carriers. The Wright Aeronautical Corporation, a successor to the original Wright Brothers Company, used their aviation expertise to create the first reliable radial engine for the Navy, the J5 Whirlwind. The J5 was put on display for the entire world to see when Charles Lindbergh crossed the Atlantic in his Spirit of St. Louis in 1927. His flight solidified the reputation of the J5 radial as a dependable power plant. The budding airlines of the world were looking for engines to power their airliners and to bring their passengers across continents and eventually across the globe safely. Reliable radial engines seemed to be the ideal choice. Radials would power many of the principal airliners in the history of civil aviation, from the Ford Trimotor to the Boeing 247 to the Lockheed Model 10 Electra. Both the U.S. Navy and U.S. Army Air Corps would rely heavily on radial engines as they built up their inventories of fighters and other aircraft. In the 1930s, the U.S. had just one inline engine in development, the Allison V-1710, an engine that would one day power some of America's great fighters. At the time, relying on radials seemed a prudent decision, but in the years to come, and in the battles ahead, it will leave the U.S. playing catch-up with their allies and enemies in Europe. In Europe in the 1930s, air forces and aircraft manufacturers were looking for speed above all else as they designed the next generation of fighters. Using streamlined designs and powerful V12 inline engines, they pushed their aircraft to speeds over 350 miles per hour. Their inline engines were not only more powerful, they also helped to create more aerodynamic airframes. Their elongated shapes allowed for more streamlined designs as compared with radials. Inline engines may have been more vulnerable to attack due to their complex liquid cooling systems, but no matter how durable a radial engine is, speed kills in a dogfight. Inline engines were built to provide just that. It was from this European obsession with speed that some of the legendary fighters of World War II were born, including the Supermarine Spitfire, the Hawker Hurricane, and the Messerschmitt Bf-109. Beneath their elegant frames purred ever more powerful inline engines from Rolls-Royce and Daimler-Benz respectively. In the middle of 1940, the pilots of the RAF tested their mettle and the endurance of their fighting machines in some of the most spectacular air battles of World War II. Vice-Fuhrer Göring had promised to destroy the RAF and thus facilitate the invasion of Britain. Göring had at his disposal an armada of medium bombers protected by a deadly fighter force. The result of the Battle of Britain during those few vital months of 1940 is well known. There was a heavy toll in fighters and pilots on both sides. British and German engineers tried to squeeze every ounce of power from their engines. Any tiny advantage could be the difference between life and death. With Britain and her industry under direct attack, she looked to her old colony more than ever to provide her with desperately needed aircraft. Even before the Battle of Britain, the British Purchasing Commission had already been shopping for additional aircraft. The US's initial offer of fighters was not well suited for the high-altitude dogfights taking place over Europe. This was partially due to the American engines available. The US had concentrated on radial engine production instead of inline engines like the ones so popular in European fighters. They did have the Allison engine, the V-1710. Like the British Rolls-Royce Merlin, it was a 12-cylinder inline engine, but it had a complex turbocharger often difficult to fit into an aircraft. To boost power in the thin air at high altitudes, the Allison engine used the heat of its exhaust to power a turbine and thereby increase the airflow and power. One American aircraft, the Lockheed P-38, had the extra space needed to house the turbocharger. It was a big twin-engined aircraft to begin with and had space in its tail booms for the extra equipment. But given the size of the P-38, it wouldn't have fared well against nimble single-engine German fighters in a dogfight. America had other smaller fighters powered by the Allison engine, the P-39 Airacobra and the Curtiss P-40 Warhawk. In both cases, their manufacturers failed to include Allison's turbocharger. The P-39 had an innovative layout, with its engine situated mid-fuselage, behind the pilot. It was designed to house both the Allison engine and the turbocharger. However, a scoop built into the left side of the fuselage to cool the turbocharger was deemed too aerodynamically expensive. Both the scoop and the turbocharger were eliminated from the production design. This change crippled the Aerocobra's ability to fight at high altitudes. In the case of the P-40 Warhawk, a rugged, single-engined airplane, the turbocharger was excluded from the design from the get-go. This limited its optimal altitude to just 15,000 feet, and thus relegated the aircraft to ground attack work. The British Purchasing Commission was still interested in the Warhawk, even with its limitations. They saw it as more of an Army support aircraft. However, the Curtiss factory was running at capacity and could not fulfill the order. With no suitable aircraft readily available for purchase, the Brits would turn to North American aircraft. The British Purchasing Commission proposed that North American build the Warhawk under license from Curtiss. But NAA President Dutch Kindleberger had a bolder plan. He guaranteed that he could create an even better airplane, using the same Allison engine, in less time than it would take for him to retool for Warhawk production. The Brits said yes, and the end result was an airplane that may well have changed the outcome of the Second World War in Europe. Back in Europe, Germany was looking for an aircraft to augment the Bf-109. In the Battle of Britain, the Bf-109 and Spitfire were closely matched. But the Bf-109 lacked the range to be highly effective in its escort role over Britain in the summer of 1940. The Luftwaffe had a twin-engined escort, the Bf-110. It had the range to be an excellent escort, but it lacked the maneuverability to defend itself or its charge in a dogfight. It also used two Daimler-Benz 605 engines, making it an expensive sitting duck for British interceptors. Looking for a quick solution to their escort dilemma, the Luftwaffe even considered having the 110s tow 109s into battle to conserve fuel. But in the long run, using two aircraft to perform the role of a single fighter was an even more wasteful solution. What the Luftwaffe needed was a dedicated single-engine aircraft to fill in for the Bf-109 on longer-range missions. And ideally, something to give them a decided advantage over the British fighters of the time. However, the Luftwaffe wanted to have its cake and eat it too. They wanted a new fighter, but they didn't want to sacrifice any of the precious 605 engines meant for the Bf-109. To the consternation of the Luftwaffe, most of the new submissions for fighter designs from German industry were to be built around this very same engine. To solve Germany's escort woes, one man, Kurt Tank, Focke-Wulf's legendary designer and test pilot, did what was almost unthinkable at the time. Since the start of the war, British and German designers had relied upon powerful 12-cylinder inline engines to power their fighters. Tank dared to build Germany's next fighter around a bomber's radial engine. The air-cooled BMW 801 radial engine had plenty of power and had proven reliable in the Ju-88 and Do-217. But radials in a fighter were a rare sight in Europe. It was difficult to build this aerodynamic a fuselage to house them in as when constructing one for a slender inline engine. Though an unconventional design track, Tank saw two reasons for encouragement. Firstly, the National Advisory Committee for Aeronautics in the U.S. had already done research on improving airflow around radial engines. Over time, they had developed the NACA cowl, which at least helped to reduce drag. This was a simple ring which fitted snugly around the cylinders of a radial engine. It not only made the engine more aerodynamic, it also improved cooling. Secondly, Tank observed that the US and Japanese navies were employing several modern carrier aircraft, all with radial engines. Aircraft like the F-4F Hellcat and the Japanese A6M Zero. The lightweight Zero had been almost unstoppable in the early part of the Pacific War. Tank had continued to explore ways of improving his new radial-engined aircraft and reducing the drag effect, although some say his greatest task was selling the radial idea to the ministry. If that was the case, the bureaucrats must have been quickly won over by Kurt Tank's first prototypes. Given the designation the Focke-Wulf 190, and unofficially known as the Butcherbird, the Luftwaffe's latest fighter was rushed into production. Fortunately for the Allies, the FW-190 arrived after the close of the Battle of Britain. In the summer of 1941, 5 Mark V Spitfires flying over the south coast spotted several radial engine fighters in German markings. At first glance, they were mistaken for US-built Republic Lancers. It was a deadly case of mistaken identity. The aircraft were, in reality, early model FW-190s. The Spitfire pilots who survived the ensuing battle lived to tell just how quickly their comrades had been lost. But Britain's greatest loss that day was not pilots or planes. The battle marked the day Britain lost air superiority to the Luftwaffe. The RAF had to do something, and fast. All eyes looked to Rolls-Royce, manufacturer of the Merlin engine, the power plant of the Spitfire, Hurricane, and so many of Britain's great planes. Although the company had the next-generation engine, the 12-cylinder Griffin in development, it was well over a year away, more than enough time for Britain to lose the war. Earlier, there had been some thought given to modifying a few Merlin engines for experimental high-altitude work to be executed by a Wellington bomber. It was little more than an idea at the time, but in Britain's hour of desperate need, Rolls-Royce engineers worked night and day to test the concept. Merlin engines were already supercharged. An air compressor mechanically attached to the rotating camshaft increased the airflow to the engine, allowing it to burn more fuel and to boost performance. Rolls-Royce engineers had theorized that adding a second supercharger could give the engine even more punch during high-altitude work. Might a two-stage supercharger help the RAF reclaim air supremacy? The end result of the Rolls-Royce experiments was breathtaking. It was almost as if the two-stage, two-speed Merlin was an entirely different engine, when in fact it was just a modification. When the double supercharged aircraft, dubbed the Spitfire Mark IX, finally arrived in June of 1942, the RAF had a rare opportunity to test it directly against a captured FW-190. The test results were far different than the day a group of unlucky RAF pilots ran into a flock of butcherbirds. The two aircraft were virtual equals in terms of performance. Captain Eric Brown, who had flown a captured FW-190, had a chance to test the new Spitfire 9 against the German aircraft in live combat.
I'd flown the 190 quite a bit, so I wasn't too frightened. I reckoned I knew what that aircraft could do, and I knew what my Spit could do, so I thought, well, I can handle this guy. Hoping he was somebody just out of training school, but no, I picked somebody who really knew what he was up to. And we had, I would say, a touring and throwing over France. but neither could get a draw bead on the other. We finally realized, as both of us, we've run out of fuel. We waggled our wings at each other and departed. And I realized this was really a top-notch fighter aircraft.
The RAF had leveled the playing field with the Luftwaffe, at least for the time being. But what the RAF really needed was an aircraft to give them the upper hand. The new Merlin's greatest contribution to the war was still to come, when it was mated with an extraordinary aircraft of American design. Back in the U.S., North American Aircraft had continued to work on a Warhawk substitute, which met the specifications laid out by the British Purchasing Commission. They had specified that the airplane be powered by an Allison engine, that it cost less than $40,000, and that it be armed with 4 .303-inch machine guns. North American answered with the P-51 Mustang. It featured an advanced laminar flow wing for good aerodynamic efficiency and a wide gate undercarriage for safer landing. Pleasing to the eye and to fly, although mainly at lower altitudes, the new arrival quickly gained respect from pilots and ground crews alike. There were some concerns about how the Mustang would fare should it be forced to ditch while crossing the channel. During a water landing, its air scoop, located beneath the fuselage, might flood the aircraft or cause it to overturn. Water tank tests at Saunders Row were initiated to perfect the techniques for ditching the aircraft. Around the same time that the RAF was getting the Spitfire Mark IX ready for combat, and the FW-190 was dominating the skies, Rolls-Royce test pilot Ronald Hawker was tasked with the mission of evaluating all aircraft powered by non-Rolls-Royce engines. He was thoroughly impressed with the P-51A, save for its poor performance at high altitude. Like the P-40 Warhawk, it had an Allison engine and no turbocharger. Hawker pondered how the aircraft might perform with the new Merlin engine. The results on paper were phenomenal. According to Rolls-Royce's calculations, with a Merlin power plant, the Mustang would not only outclass any American aircraft, but even new Spitfires using the same engine. Oddly, Hawker had to push for the mating of the Merlin 61 and the Mustang, even though the double supercharged P-51 would have outclassed the FW-190 as well. Hawker finally arranged for the marriage of the two great inventions, and test trials confirmed his hunch. The Mustang was a war winner. The main challenge was to produce enough aircraft and engines to reclaim the skies of Europe. North American would tweak the Mustang design to accommodate the Merlin 61 engine. It was a much more powerful engine, so the original P-51A airframe had to be reinforced. As well, the three-bladed prop was exchanged for one with four blades. The addition of plumbing for drop tanks might have seemed a small change, but it would have a great impact on the air battles to come. Packard took up manufacture of the Merlin 61 engines in the U.S. They were designated the V-1650s. Packard had arranged a licensing agreement with Rolls-Royce earlier in the war. Ford was originally slated to build American-made Merlins and seemed a perfect choice due to the company's industrial might. But Henry Ford was adamant that his company build defensive weapons only. North American's double supercharged aircraft, the P-51B and P-51C, first took flight in the spring and summer of 1943. Air Vice Marshal Paddy Harbison recalls when the Mustangs first arrived at his Spitfire squadron.
Well, of course, the Mustang was a revelation. It was a much more comfortable airplane than the Spitfire was. And I have heard people talk about the relative merits of both. They were both war winners. The Spitfire was meant as an interceptor. It could outturn a Mustang and it could outclimb it, but it didn't have the legs the Mustang had. And of course, if you can't get to where the fight is, you're not too effective.
As P-51 started to arrive in Europe, the war was changing, and the Mustang was the perfect aircraft for the time. The U.S. was taking the war to Germany. They were bombing the German war industry out of business. The only problem was their bombers were being shredded by speedy German interceptors. The U.S. had hinged their hopes on the ability of their bombers to defend themselves by maintaining a tight box formation. When this strategy failed, they were in dire need of an escort fighter. The P-38 Lightning was simply not agile enough to take on the role. Then there was the P-47 Thunderbolt. It was an awesome radial engine fighter, more than capable of taking care of itself in battle. But it had two major flaws. It was expensive, and it lacked the range to take the bombers all the way to Berlin and back. The P-51Bs and Cs arrived just in time. They had been designed to carry drop tanks, and with the addition of a fuel tank behind the pilots, they had more than enough fuel to escort American bombers to Hitler's lair. The Mustang proved more than a match for Germany's FW-19 and Me-109. Slowly, American bombers closed in around Berlin. Suddenly, the Germans found themselves playing catch-up. Kurt Tank's FW-19 with a radial engine found it difficult at higher altitudes where the bombers roamed. Tank swapped its radial engine for an inline. The long-nosed aircraft was nicknamed the Dora.
The Focke-Wulf Dora, the later Dora, was a magnificent fighter with an engine change, not really any structural changes other than those to accommodate the engine. But what it meant was, here was an airplane that could keep up with the hunt as the years of the war progressed. So from 1942 right up to the end of the war, the Focke-Wulf 190 was in the top grade of fighter or fighter bomber.
The P-51 Mustang also continued to evolve as mechanics and engineers incorporated changes based on the feedback of pilots who had tested the plane in battle. Its canopy went through several permutations. The British swapped the original one for a sliding Malcolm hood, similar to a Spitfire's for improved visibility. The P-51D, the definitive version of the Mustang, had a bubble canopy, which offered 360 degrees of clear view. North American also upgraded the D's firepower. It had 650 caliber machine guns compared to 4 in earlier models, and it had solved the problem of gun jamming during hard turns. The fuel tank situated behind the pilot may have increased range, but it created other issues. The plane had poor directional stability when the tank was full. To counter this problem, engineers added a small dorsal fin in the D model. These and other improvements would help the Mustang blaze a path to Berlin for America's bombers. Reichsmarshal Hermann Göring, commander of the Luftwaffe, was quoted as saying, "When I saw Mustangs over Berlin, I knew the jig was up." When the European war had come to a close, the battle still raged in the Pacific. The Mustang was the best escort available, but even with its incredible range, it could not accompany an aircraft like the B-29 Superfortress on extended bombing missions over Japan. The expanses of ocean were too large. The engineers at North American struggled with the problem of stretching the Mustang's range. Their solution was a Zwilling or twin Mustang. By fusing two Mustangs together, they hoped to dramatically increase the range of the Mustang while retaining its excellent dogfighting abilities. The new Mustang, the F-82, had an incredible range, 2,000 miles. Though the prototypes were powered by Packard-built Merlin engines, the U.S. Army Air Corps was adamant that the production version be totally American-made. Unfortunately for the F-82, without Merlin engines, it was not the same aircraft. When fitted with the Allison V-1710-100, its speed dropped and high-altitude performance suffered. It was one of the few cases of a prototype outperforming the production model of an aircraft. By the time the F-82 was ready, Japan had surrendered, and the war was over. After the war, the P-51 continued to serve, while other piston engine fighters of the era went quietly into retirement. Though it was the dawn of the jet age, there was still a place for the Mustang in a variety of roles. Colonel Ray O. Roberts flew the Mustang during its second life.
At that time, I was flying what they call the F6, which is a P-51 with cameras. Also had guns, and you could have the bombing and gunnery capability. And we participated in a post-hostilities mapping program. We revised all the Japanese maps, photographed, did aerial photography in Japan and Korea.
When the Korean War arrived, Mustangs which had been mothballed for long-term storage were suddenly being shipped across the Pacific on carriers. Unable to compete with the next generation of jet fighters for the dogfighter role, Mustangs returned to where they started. In Korea, Mustangs made excellent ground attack aircraft. They didn't have the speed of jets, but they had the endurance to make it from Japan to Korea on bombing runs. In Korea, the F-82 also had an opportunity to taste combat for the first time. F-82s flew strike, escort, and night fighter missions. The marriage of the P-51 Mustang and the Merlin 61 engine produced incredible results. It provided the Allies with an effective escort to pound the last nails into Germany's coffin. Perhaps the most amazing thing about the P-51's stellar career is that it might never have happened. If the Merlin and Mustang had never been mated at the suggestion of Hawker at Rolls-Royce, the P-51 might have had a humdrum career as a reliable ground attack aircraft, rather than an elite dogfighter. It arrived at the right time and the right place in history, just when the Allies needed an escort fighter. The P-51 was the end result of years of aircraft and engine development. Though jet-powered aircraft would supplant it, the impact of the Mustang and Merlin in military history cannot be unwritten or denied.
At the Farnborough Air Show in 1949, barely 4 years after the war ended, Britain presented an impressive array of jet aircraft. Some were purely military, others experimental, and there were even some airliners converted from piston engines to the new jet technology. Perhaps the best crowd pleaser was the advanced de Havilland Comet turbojet airliner. Elsewhere in England, other types of jet airliners were being developed, but these were somewhat different. This is the Vickers Viscount airliner. When it first came into service in the early 50s, it quickly became a success. One of the main reasons for the Viscount's ever-expanding order book was the aircraft's Rolls-Royce Dart turboprop engines. However, the Viscount wasn't the only contender, nor was the Dart the only turboprop engine available at the time. Slightly smaller than the Viscount and with different turboprop engines, the Armstrong-Whitworth AW-55 Apollo was no less pleasing to the eye, and in tandem with the Vickers aircraft, represented a giant step forward in airline design. The target market for both aircraft was the short to medium routes of the emerging post-war airline industry. With government backing British industry, they had something special to offer with the revolutionary turboprop engines. The concept of a conventional jet having its exhaust thrust converted into turning power for traditional propeller blades was brand new, and it made for extremely economical and very smooth running. There were two early examples, the Rolls-Royce Dart and the competitive Armstrong-Siddeley Mamba. The Apollo's designers favored the Mamba, whereas Vickers chose the Dart. Construction of the Apollo started in Armstrong-Whitworth's factory at Baggington Airport in 1948. Baggington had been bombed during the German Blitz on Coventry. It was used as an RAF fighter base during the war years, but now it would be used as part of Britain's critical export drive to repay the war debt. There were grounds for optimism as the country refocused its industry. Only 3 years earlier, Manufacturers had produced Spitfires and Lancasters by the thousands, and for a time, most of the skilled aircraft builders were still on hand. One of the more notable features of the Apollo's Mamba engines was their narrow diameter. Slender and aerodynamic, they complemented the aircraft's aesthetics. However, the smaller engine housings that accompanied the Mamba did not provide for an area to store the landing gear in flight. This meant that the main wheels had to retract into the fuselage, consuming valuable space. However, the Mamba still showed great promise. Apart from anything else, it had already powered a trainer, the Athena, which was actually the first production aircraft to employ a turboprop engine. Also, early tests suggested good performance. In 1948, a 500-hour test run confirmed the engine's durability. After this, Armstrong and Whitworth were sure that they had a winning combination. The AW-55 Apollo prototype was designed and built to accommodate a crew of 3, 2 pilots and 1 cabin crew. Passenger seating could be configured for up to 31 people. However, a slightly longer version for production had also been discussed, as well as a military version for troop transport. Construction on the Apollo progressed until its rollout in April of 1949. This sleek, fully pressurized airliner was a far cry from the utility fighters and bombers the industry had produced just a few years before. On the 10th of April, Apollo aircraft serial number VX-220 took to the air from a grass field at Baggington Airport. Its first flight lasted just half an hour, and the results were less than impressive. The first problem was that the Mamba ASM-2 engines failed to produce the 1,200-plus horsepower expected, which were indeed needed to meet the aircraft's performance requirements. The 800 horsepower that was actually recorded was far short of what was anticipated. Subsequent test flights also demonstrated numerous flaws in the airframe design. Improvements were constantly made until a critical flight test to Paris and back was undertaken on the 12th of March, 1951. Still, problems persisted, with the Apollo having a flawed airframe and the Mamba engines remaining underpowered. In June of 1952, all further development on the Apollo was abandoned, and the only 2 examples ever built were used for research work at Boscombe Down. This left the Vickers Viscount the undoubted winner, and it was this type that also went on to become one of Britain's all-time airliner export earners, with 445 built. The redoubtable Rolls-Royce Dart turboprop engine was even more successful, with over 7,000 engines delivered to numerous customers up until 1987, 41 years after its first test. For a while, the Armstrong-Siddeley Mamba had no such success, but then again it certainly wasn't a complete failure either. Rather, with improvement, it morphed into several different life forms, each one displaying considerable and unexpected ingenuity. At about the same time that the Apollo was under construction, the Royal Navy and Fairey Aviation were developing a truly remarkable anti-submarine aircraft. The Fairey Gannet shared the same problems as many carrier-borne aircraft. It had the performance needs of 2 power plants, but this usually meant the high risk of possibly having to land with one engine not functioning. This type of asymmetric approach is highly dangerous for the aircrew. The second consideration for Fairey's designers was the significant economy that might be achieved on long missions if one of 2 engines could actually be turned off, and yet still leave the plane with the same balance as a single-engined aircraft. Armstrong-Siddeley thought that they might have the answer. The very narrow diameter of the Mamba turboprop might now prove most useful if 2 could be assembled side by side, driving 2 contra-rotating propellers, both able to be turned on and off independent of the other. The double Mamba, as it became known, was a major success, providing Gannet pilots with 2 jet power plants in an aircraft that had great range and at the same time was safe to land even with one engine down. Because of its Mamba engines, the Gannet became a much trusted maritime aircraft, which went on to serve in a number of other countries. With nearly 350 of all types made, it wasn't so far off the numbers of Viscounts delivered, although the Vickers plane had 4 turboprops as opposed to the Gannet's 2. Still, the versatile Mamba had much more to offer. By removing the gearbox and the propeller drive, Armstrong Siddeley were able to present a conventional turbojet. With a few more deletions and economies, this evolved into a so-called expendable power plant, and it transpired that there actually was quite a market for a short-life jet engine. It was named the Adder. Post-war Western governments knew that they might have to deal with Soviet forces that would include jet aircraft. Target practice on anything flying less than in the high 500 miles an hour range would be useless. Equally important, a target would have to be able to fly up to a height of 50,000 feet and get there quickly, since most drones only have a limited flight time. In 1948, the Australian Government Aircraft Factory entered into a contract to develop an unmanned radio-controlled flying target. It was given the name Jindavik, Aboriginal for the hunted one. Made in Australia, many were shipped to Britain in parts, where, with their experience with the Mamba engine, Fairey Aviation assembled each unit that was powered by the Mamba's descendant, the Adder. More than 500 Jindaviks were built and employed by Australia, Britain, the United States, and Sweden. Over time, Armstrong Siddeley merged with their rivals, Rolls-Royce, although not before it had redeveloped the Adder into a stronger and more reliable turbojet. The end result was also much more powerful. It was named the Viper, and Vipers were produced in the hundreds, powering the Jet Provost, Strike Masters, Hawker Siddeley 125, and many more. What started out as a misfire with the Mamba engines on the Apollo developed over time into a successful line of engines with the double Mamba, Adder, and Vipers that would power numerous aircraft for years to come.
One problem facing the designers of the next generation of turbojet engines is that of increasing turbine inlet temperatures. Air-cooled turbine blades may offer a solution to this problem. The fabrication of a cast air-cooled turbine blade that has shown promise in prototype testing will be shown in this film. This blade was made using a modification of the lost wax casting technique, a process to provide long, slender holes for cooling passages was developed by the Lewis Flight Propulsion Laboratory of the National Advisory Committee for Aeronautics. This development is particularly important because the superalloys used in aircraft turbine blades are extremely difficult to machine. Ceramic tubes are used as part of the casting mold to establish cores or holes through the turbine blade casting. Core tubes of the desired outside diameter are assembled in a pattern die. The core tubes are held in place by embedding them in a bar of soft wax using a hot wire or knife. The dies used are made of a low-melting alloy cast around a brass master pattern. A casting pattern is made by closing the dies containing the ceramic tubes, clamping the dies in a wax injection machine, and injecting molten wax under pressure. The wax pattern containing ceramic tubes is removed from the die, and excess wax is trimmed, leaving a light wax film on the exposed ceramic tubes to permit freedom of movement due to expansion. Additional pieces of wax are assembled by welding with a hot wire. These pieces will form sprues, runners, and ingates or passages for the molten metal to reach the blade cavity in the casting mold. The assembled wax is mounted on a waxed base to seal it. A can-type flask is placed over the assembly
and it too is sealed at the bottom. When the investment is thoroughly mixed, it is poured into the flask and around the wax pattern assembly. The flask is then placed in a vacuum chamber to remove air from the mix. After investing and air drying, the molds are placed in a furnace. Here the drying is completed, the wax is melted out, the wax residue is burned off, and the mold is cured. During this furnace cycle, the temperature is gradually increased from room temperature to 1900 degrees Fahrenheit. Metal alloy for the casting is melted in an electric induction furnace. When the metal reaches a temperature of 3000 degrees Fahrenheit, the crucible of molten metal is placed in a centrifugal casting machine, and the hot mold is placed over it. As the casting machine is spun, the molten metal is thrown into the mold. The casting is removed by breaking away the mold. After the casting is cleaned up, the ceramic tubes used to form the cooling passages in the blade must be removed. This is done by threading fine stainless steel wires through each ceramic tube and stretching them taut on a frame. The turbine blade is then attached to a cam device designed to slide the blade up and down on the wires. The lower part of the assembly is then immersed in a bath of molten caustic. This helps to remove reaction products and introduces fresh caustic to the bore of the tubes, and hence accelerates the solution and removal of the core tubes. The rough casting is cleaned in an air-water abrasive blast. A suitable base configuration is then ground, and the blade is ready for testing in a research facility. The process you have just seen illustrates a principle that has been effective in producing long, thin-cored holes in castings. This process may be useful in fabricating turbine blades to be used at very high turbine inlet temperatures.
The F-100 is one of our primary tactical support weapons systems. This aircraft has a proven history of outstanding performance. One of the reasons for this dependability is the rugged power plant. The F-1, a high-performance aircraft, is adaptable to many missions. It is used for reconnaissance, as a tactical fighter, and as an interceptor. Approximately 30,000 pounds of thrust is developed by its twin engine. The F-102 is the first operational Air Force Delta Wing aircraft. The performance characteristics of this weapon system are ideally suited for intercept missions. A reliable power plant is essential for the success of any mission. The F-102, 101, and 100 are all powered by the rugged J57 engine developed by Pratt Whitney. The individual engines vary somewhat, but for the most part are the same fundamental design. The J57 is a dual compressor engine. The engine consists of the following components: the inlet, the low-pressure compressor, the high-pressure compressor, the diffuser case, combustion chamber, the first, second, and third stage turbines, the afterburner, and the exhaust nozzle. The low-pressure compressor, referred to as N1, is driven by the second and third stage turbines. The high-pressure compressor, N2, is driven by the first stage turbine. These two units, or spools, are not mechanically connected. The J57 operates on the same basic principle as all jet engines. Pressure, presented in graph form below the basic engine outline, and velocity are increased by a series of rotors in the compressor section. A compressor bleed system prevents compressor instability when the engine is operating at reduced power. The compressed air passes through the diffuser into the combustion chamber, where the air expands, thus reducing somewhat the velocity and pressure. Fuel is mixed with a portion of the air to form form the combustible mass. When combustion occurs, the gases are expelled through the turbine. At this point, power is extracted by the turbines to drive the compressors. The remaining energy, expelled through the exhaust nozzle, provides the thrust. Since exhaust nozzle and turbine discharge pressures are relative, turbine discharge pressure is used as a parameter to determine thrust. Thrust is the measure of force developed by the engine. Force is determined by mass times acceleration. Mass is the weight of air and fuel passing through the engine. Acceleration is the difference between inlet and turbine discharge velocities of this mass. Thus, thrust may be expressed by the formula force equals mass times acceleration. The engine trim charts are based on this formula. Additional thrust is obtained in the afterburner by increasing mass and acceleration at that stage. The basic engine pressure ratio during afterburner operation is maintained by increasing the exhaust nozzle area. Efficient engine operation depends on correct fuel schedule. The basic components of the J57 main engine fuel system are fuel pump and fuel pump transfer valve, fuel control, and the pressurizing and dump valve. The fuel pump is a dual-element spur gear pump. One element supplies fuel to the afterburner, the other to the main engine. The fuel control meters the fuel required to operate the engine through its full range. The pressurizing and dump valve supplies the main engine fuel manifold and drains the manifold at engine shutdown. At engine start, fuel enters the pump through the impeller where the pressure is increased. This provides a positive pressure head to the main stage. At this stage, the fuel reaches output pressure. The pressurized fuel closes the fuel regulating transfer valve and the afterburner check valve and flows into the fuel control. The main metering valve is closed at this time. A portion of this fuel passes through the minimum flow orifice through the signal line to the P&D valve. Since the control is in bypass, pressure does not build up enough to close this valve until the power lever moves from cutoff to idle. When the power lever is moved to the idle position, the fuel dump valve closes. The main metering valve opens. The cutoff valve moves off its seat. The pressure loading valve opens. The P&D valve inlet check valve opens. And fuel is supplied to the primary side of the fuel manifold through the pressurizing and dump valve. At approximately 74% RPM, the fuel pressurizing valve will open to supply fuel to the secondary side of the fuel manifold. The J57 engine uses a primary and secondary system in order to obtain the highest possible fuel flow with the shortest possible flame. At low RPMs, only the primary side is used. When the emergency system is selected, the actuator positions the pilot valve to direct pressure to the shuttle valve system. The shuttle valve blocks off metered flow and provides a port for unmetered fuel to the emergency throttle valve. This mechanical valve controls the flow of fuel. The afterburner element of the fuel pump will supply fuel to the engine in the event of main element failure. The primary function is to furnish fuel for the afterburner. The other components of the J57 afterburner system are the afterburner fuel control, exhaust nozzle control, igniter valve, and the mechanical shutoff valve. The relative position of the components varies according to engine model. The afterburner fuel control meters fuel to the AB spray box. The exhaust nozzle control directs compressor discharge air to open and close the nozzles. The igniter valve injects fuel into the combustion chamber, creating a streak of flame to ignite the afterburner. In the event of electrical failure, the mechanical shutoff valve will terminate AB operation at approximately 80% RPM. Rotation of this valve causes AB stage fuel to bypass through the AB fuel control regulator valve. The fuel control unit is carefully calibrated on the test bench to assure accurate engine fuel schedule. The main functions of the fuel control are to maintain acceleration schedules below compressor stall zone, to prevent over-temperature during acceleration, prevent lean die-out during deceleration, and to maintain any selected engine speed within operating limits, regardless of altitude. The fuel control senses engine RPM, inlet temperature, and burner pressure to supply the correct amount of fuel for any ambient condition. When calibration has been completed, all external adjustments, except the idle and military trim screws, are sealed. These seals are installed to protect test bench precision calibrations and must not be removed. The J57 engine will provide relatively trouble-free operation when all systems are functioning correctly. However, the systems must be properly rigged and adjusted. One of the most critical engine adjustments is the rigging of the fuel control linkage. Full range movement is obtained only when the fuel control and afterburner mechanical shutoff valve levers are correctly positioned. The levers are set to predetermined angles. A protractor or etched template is used to set the linkage at these angles. The protractor is positioned at the oil pump and accessory housing plug to establish a reference angle. This reference angle will be used to adjust the fuel control lever. With the fuel control lever in cutoff position, the difference between the reference angle and this reading must be the number of degrees specified in the tech manual. It may be necessary to readjust the fuel control lever to obtain the correct angle. The fuel control lever and serrated spacer are ratcheted to give the desired angle. The fuel control position, which, when all other linkage is connected, will close the afterburner mechanical shutoff valve. The power actuating rod is then attached to the fuel control lever. Move the mechanical shutoff lever to the detent position. The rod, connecting the cross shaft lever and mechanical shutoff valve lever, may have to be adjusted to the specified length. The AB mechanical shutoff valve is held in detent position, while the lever is ratcheted to the position where the rod, which has already been adjusted to the specified length, will fit. Then all connections are tightened. Either the protractor or an etched template is used to again check the angle of the fuel control lever. It may be necessary to readjust the fuel control lever to obtain the correct angle. After corrections are made, all connections are then safety. Replacement or adjustment of most components will affect engine operation. Prior to aircraft installation, the engine is thoroughly inspected and tested to ensure satisfactory performance. A fuel leak check is imperative before initial start of a repaired engine. With the system pressurized, check all fuel lines and connections. The exhaust nozzle opening must also be rechecked before initial engine start. Nozzle diameter not within specified limits will affect engine efficiency. On some engines, a fail-safe device is installed to prevent total loss of power in the event of linkage failure. The device will position the fuel control lever to a 45-degree angle setting, which will provide approximately 90% RPM, thus ensuring sufficient thrust to maintain flight. After installation in the aircraft, all airframe to engine connections must be checked and adjusted, and the engine retrimmed. Final trim, to compensate for aircraft installation losses, is preferably accomplished with the aircraft headed directly into the wind. Prevailing wind velocity and direction must be within limits specified in the tech manual. The trim pad area must be free of loose objects that could damage the engine if ingested. To effectively trim the engine, power control settings must be coordinated. Throttle linkage is operationally tested before making fuel control adjustments. Movement of the fuel control quadrant must synchronize with throttle movement. Power control movement is transferred to obtain predetermined fuel control settings. The aircraft manual indicates the relative degree of movement throughout the entire throttle range. Close attention to detail is required when trimming an engine. Changes in ambient barometric pressure and temperature will affect engine performance characteristics. True barometric pressure and correct temperature, both recorded within 15 minutes of the trim run, are used to determine target PP7. Target PP7 is obtained by tracing the temperature and pressure coordinates on the trim chart. Start engine is specified in the tech manual and allow engine and exhaust gas temperature to stabilize. Retard throttle to idle setting. Desired idle speed is obtained by adjusting the idle trim screw. As in all fuel control adjustments, final trim is always in the increased RPM direction. Proceeding with the trim operations, slowly advance throttle to military power. Allow 5 minutes for stabilizing. Caution, do not overspeed or overtemp engine during run-up and stabilization. With throttle set at military power, record RPM, EGT, and the turbine discharge pressure, PP7. If PP7 reading is low, return throttle to idle and readjust maximum RPM setting at the fuel control. Turn the adjustment clockwise to increase RPM in order to obtain target PP7. Advance throttle to military power. Stabilize, then recheck PP7. Return throttle to idle. Check EGT and RPM. Make certain that RPM is within 2% of data plate speed indication. At the completion of the trim run, follow standard shutdown procedures. Accurate troubleshooting depends on a thorough understanding of the J57 engine and its system's functions. Only by correct analysis of the interrelated parameters can the malfunction be isolated. Proficient troubleshooting is the mark of quality. The Tech Manual outlines the common symptoms of engine malfunctions, the probable causes, and their remedies. Basic parameters used to determine engine performance must also be considered when analyzing problems. These basic parameters are RPM, PT7, and EGT. One of the most detrimental engine malfunctions is overtemping, or high EGT. Perform static checks of PT7 lines and connections and the exhaust nozzle opening. Make sure the anti-icing valves are closed. Then check for instrument accuracy. All static checks have been performed and found satisfactory. Now the engine must be checked for proper trim. As engine approaches military power, check exhaust nozzle for creep. Check to make sure that PT7 has not exceeded target and RPM is within data plate limits. If high EGT still exists, the engine must be removed and a hot section inspection must be performed. Inspect the burner cans for cracks or hot spots. Check fuel nozzles for loose, burned, or missing air caps, and evidence of seal leaks or clogged air holes. Check the first stage turbine nozzle guide vanes for excessive bow. Turbine vanes bowed beyond limits will distort the gas path, causing loss of turbine efficiency. The amount of fuel required to compensate for this loss accounts for the excess temperature. In conjunction with correction of the bowed nozzle guide vanes, or providing they were within limits, additional checks are necessary to assure the problem is corrected. Inspect first and second stage outer air seals for cracks, burned areas, and damage to outer knife edges. Check clearance between outer air seals and turbine blade shrouds. Check first stage turbine dislocating dimensions. The cause of high EGT may have been one major problem isolated at any phase of the investigation, or the accumulation of minor deficiencies requiring several procedures to isolate and correct. Had RPM exceeded data plate limits during initial high EGT troubleshooting trim run, the engine would have to be fuel cleaned before proceeding with other checks. This process is intended to restore compressor efficiency. When this operation is completed, retrimming the engine may bring all parameters within limits. troubleshooting engine performance deficiencies, it is necessary to consider all three parameters: EGT, RPM, and PT7. As an example, failure to obtain target PT7 can be caused by many things. By comparing the relationship to EGT and RPM, many unnecessary troubleshooting steps can be eliminated. For instance, when all three parameters are low, a fuel scheduling deficiency is indicated. First, check for full travel of the power lever to fuel control quadrant. Military position must not be less than 54 degrees. The next step is to remove the fuel control and check the position of the camshaft. With camshaft cover removed, lever positioned at 11 degrees, and the temperature sense bulb in a 60-degree Fahrenheit bath, measure the distance from the end of camshaft to the cover flange. This reading should coincide with that on the camshaft depth plate. Tolerances and replacement instruction are included in the engine tech manual. The engine tech manual includes specific instructions for maintenance procedures. These manuals represent a vast accumulation of knowledge and experience. Through individual ability, initiative, and constant use of the tech manual, proper maintenance and troubleshooting procedures can be achieved. This is the goal of the Improved Maintenance Program.
I was quite astonished to know what it was because it had no propeller.
And John replied, "Oh, it's easy, old boy, it just sucks itself along like a hoover." There was the awful race against time. There was the skullduggery.
She used to say, "Oh, well, Daddy's doing something very hush-hush."
I thought, my goodness, why didn't I think of this before? And it seemed so obvious then.
A small English church is the last resting place of a man who didn't just change the face of the earth. He enabled us to see what it actually looked like. His name was Frank Whittle. This is the story of how he invented the jet engine. He overcame all the odds, only to see the British government almost throw his idea away and miss a chance to shorten the Second World War.
I was born on June the 1st, 1907 in Coventry. My parents were working class. My father was a foreman in machine tool manufacturers. I lived there in Coventry for 9 years, went to an elementary school there. And then the family moved to Leamington Spa because my father bought a small, very small engineering outfit called the Leamington Valve and Piston Ring Company. And I really did get my first engineering experiences there because I helped him sometimes for, I think it was about 2p an hour or something like that, making slots in valve stems.
In Leamington, Frank also won a scholarship to the town's secondary school.
I was very lazy with homework and got a series of raspberries for that. But at the end of term, I would often do quite well. For instance, I'd come top of maths, something like that. I never did win a prize at school. But I did an awful lot of private study. I used to go down to the library in Leamington Spa and study all sorts of things which are not in the school curriculum. And that was where I first started to learn about gas turbines. I was always attracted to flying from my earliest years almost, When I was 4, my favourite toy, and this was 1911, was a tin model of a Blériot. And my heroes were people like Captain Albert Ball and Major McCudden and so on, the VCs of the First World War, and I just wanted to fly. And also I thought that boys in the uniform of aircraft apprentices looked very good, so I decided I'd like to wear that uniform and applied to join as an apprentice.
The Royal Air Force, however, rejected young Whittle. He was too small.
I was sunk for the time being, but before I left the camp, a very kindly physical training sergeant, if you can imagine such a thing, took pity on me, and he gave me a diet to follow and a series of exercises, Max Holding exercises. I did all that for 6 months. I put on 3 inches on height and 3 inches on my chest. So I thought, well, I'll have another shot. And I wrote to the ministry, but they said, no, once you've been turned down, you've been turned down forever. I thought, well, I'd go through the whole process again as though I'd never happened, in the hope that the bureaucracy wouldn't pick it up. And I was lucky that time, and ended up at Cranwell in number 4 wing.
Whittle didn't enjoy life as an Air Force apprentice. In that rank, he would never get to fly. What brightened Whittle's life was the Model Aircraft Society, where he became the leading light at building working replicas.
So much so that the initials BWMAS, which stood for Boys Wing Model Aircraft Society, was, most people said that meant Boy Whittle's Model Aircraft Society, because we were known as Boy Whittle, Boy Smith and so forth in those days.
Whittle's skills at making model planes singled him out to the authorities. Perhaps he might be officer material.
There were to be 5 cadets selected from number 4 wing at Cranwell, and I was number 6 in the passing out list. So when the number 1 boy failed because of his eyesight, it made me eligible.
The founder of the Royal Air Force had his doubts, though.
Lord Trenchard nearly stopped it, because I hadn't been a leading boy and I hadn't made no kind of a name in sports, on which a lot of weight was put in those days.
Whittle's CO had a compelling reason to make Trenchard think again.
He thought that he'd got a mathematical genius.
It was this natural gift that got Whittle a cadetship. Less than 1% of apprentices made the huge step to join the elite in the Officers' Training College at Cranwell. Although this was next to the apprentices wing, it was socially another world, one that shared the culture of the public schools from where most of the cadets then came. In the bleak Lincolnshire countryside, Frank Whittle's life now took a new direction. Cranwell provided a very intensive education for Whittle. For the cadets, just as it is today, the highlight of the course was the flying lessons.
I learned to fly on the Avro 504K. That was a very ancient type of aeroplane, 1911 type, and it sort with a toothpick between the wheels, you know, to prevent it tipping over on its nose, which in reality it helps it to tip it over on its nose, or even turn upside down.
Whittle was soon a daring, even overconfident pilot, and one who had his fair share of accidents.
I have to confess that I wrecked 2 or 3 aeroplanes. 3 at least, yeah. The first one, I got lost and wanted to get back to Cranwell when the visibility had deteriorated very badly. It was the day, incidentally, of the cross-country run at Cranwell, which all cadets hated. And most of my fellow cadets thought I'd done it to get out of the cross-country run.
In between learning to fly and studying at Cranwell, Whittle first conceived the idea that would make him famous. It all started with a student thesis.
All cadets had to write a thesis, and I chose future developments in aircraft design, rather ambitious, and rather concentrated on the engine side. But the main thing in that thesis was that I arrived at what I now know was the well-known Breguet formula. I wasn't familiar with it at the time, connecting speed, range, engine efficiency and so forth. And to me that meant that if you wanted to go very fast and far, you would have to go very high, heights of 50,000 feet, that sort of thing, at heights where the piston engine obviously wouldn't work, and at speeds which where the propeller wouldn't work. So I started to look for a new kind of power plant.
Whittle prepared this paper during the first half of 1928, but his findings at Cranwell were the fruit of the 5 years he had by now been training there.
My Cranwell thesis, when the professor marked it, he wrote on it, in effect, he didn't really understand it, but he gave me 30 out of 30, which I thought was quite satisfactory.
Whittle envisaged flying speeds of 500 miles an hour, at a time when propeller planes struggled to reach 150. These machines were noisy and shook the pilot terribly. That's because their engines were actually car motors on a bigger scale with many moving parts. Whittle felt an aesthetic dislike for such power plants.
The problem with the piston engine as you go up height, even though you supercharge it, is that the power drops off as the air gets thinner, and there eventually comes a point where it won't generate enough power to turn itself over against its own friction.
Whittle's idea would use the same principle as a balloon filled with air. When this escapes, every child knows what happens. But it wasn't clear how an engine might recreate such a force.
I considered a piston engine driving a fan inside a hollow fuselage, and then thought, well, why not throw that piston engine away, up the compression ratio of the fan, and substitute a turbine for the piston engine? And there was the turbojet.
By now, Whittle had left Cranwell, but his search for this solution had preoccupied him ever since.
It didn't come to me out of the blue for the simple reason that I've been trying to find it for 18 months. But just the thought, get rid of the piston engine and substitute a turbine, you might say that came out of the blue. Whether I was having a bath or whatever at the time, I couldn't tell you.
Whittle's plan proposed just one moving part. This would be a shaft with a compressor, driven by a turbine at the other end. It would work like this. The compressor spins round, sucking air into combustion chambers at many times atmospheric pressure. Here, this air is mixed with vaporized fuel and ignited. The hot gas created expands through the turbine, turning the shaft, and escapes into the atmosphere. It is this continuous force which propels a jet aeroplane along. The turbojet concept brought with it so many natural advantages.
A very big factor in favour of a jet engine was that when you went up high, the air temperature was very low, very cold, and that benefited the compressor a lot. It meant that you could get much better conditions for the compressor. And the other thing is that in a normal turbine, the velocity coming out of it is wasted. In the case of the jet engine, that was completely used. After the idea had come to me, I thought, oh, my goodness, why didn't I think of this before? And it seemed so obvious then.
This was Whittle's moment of genius. He had seen the future of powered flight, and he was a pilot officer, aged just 22.
I was at the Central Flying School at Wittering, doing the flying instructors course. One of the instructors there was W.E.P. Johnson, who became a very good friend and colleague in later years, and he'd been trained as a patent agent. And he became very interested in my proposal. He thought it would work, and he helped me to draft a patent.
Have you ever patented anything? No, I don't know a thing about it. Does a patent both publish and protect? That is the whole point of patents. But one thing's essential. File a patent application before touting the thing round, otherwise you haven't a hope. I'll tell you what, let's rough out a specification now.
What? Fine, what do we do?
Well, you make a rather better sketch and I'll get on with the clever bit, the writing.
Okay.
Armed with his patent, Whittle offered his idea to industry. No one thought it could ever work.
According to the theories of the time, there was this fundamental difficulty with gas turbines, inefficient compressors, inefficient turbines, and the other big snag was the materials then existing in 1929 wouldn't stand temperatures of more than, say, about 500 degrees centigrade. But I knew, or felt pretty confident, that they would evolve in the normal course of development, and of course they did.
The positive young officer also went to London to put his revolutionary concept to the Air Ministry. Whittle fared no better when he met A. Griffith, one of the ministry's top scientists.
I went to see Dr. Griffith and another scientist at South Kensington, explained the idea. It was very coolly received. Griffith pointed out an error in my calculations, and it was all rather depressing, you know. And then after that I got a letter from the Air Ministry saying in effect that they weren't really interested and so forth. It didn't help that I hadn't then received an engineering degree.
Soon after this rejection, Whittle seemed to have more bad news.
After I completed the flying instructor's course, I very nearly got posted to number 4 FTS, Abu Sweir in Egypt. That would have been a real nail in the coffin of the jet engine if that had happened.
Fortunately, the posting was changed. Whittle remained in Britain and served a year as a flying instructor. These were happy times for him. In May 1930, he married Dorothy Lee. During this period, he also got the chance to develop his exceptional flying skills. He was now one of the RAF's best pilots, and was chosen to fly in the Hendon Air Pageants, where he thrilled spectators with his skills at crazy flying. These were the red arrows of the day, and Whittle loved entertaining the public this way. At this time in Germany, a young scientist was eagerly looking forward to his first trip in an aeroplane. His name was Hans von Ohain.
I always dreamed about the beauty of flying. My first flight with a commercial airplane, I believe it was a 3-engine Yonkers, was a great disappointment. It was so noisy and so vibratory that I felt the piston engine and propeller is not the good propulsion system. The elegance of flying is destroyed by it.
The sight of smoke rushing from chimneys inspired von Ohain to think, if that force could be created by a turbine, maybe he could make a smoother aero engine.
High speed was not the primary goal. To me, the smoothness and low noise was more the starting point of my thinking. But as I thought about it, I noticed that, as a matter of fact, it will be capable of driving the airplane faster.
Britain's Air Ministry had declined to keep Whittle's patents a secret. Freely available, they quickly made their way to Germany, just as the Nazis came to power. These patents were widely read in German aviation circles, at the same time that Hitler was rapidly building a new Luftwaffe. Whittle's idea aroused no such interest in Great Britain, and his own jet engine remained stillborn. Yet the Royal Air Force was certainly keen to nurture its inventor.
After 4 years, every general duties officer had to specialise. He was given a choice between engineering, radio, navigation, physical training and so on. But I didn't get a choice because, having been pestering the Air Ministry with inventions, they just said to me, "You will be an engineer." Though they'd stopped sending officers to Cambridge, they decided that I should go. So I went to Cambridge in September 1934 to take the mechanical sciences tripos.
Once at university, Whittle applied every piece of learning to his idea for jet propulsion.
I had got the feeling, rather, that I might be ahead of my time. With the extra knowledge I gained at Cambridge, I did become rather more aware of the difficulties.
Then this letter arrived in the post, which says, "My dear Whittle, this is just a hurried note to tell you that I have just met a man who is a bit of a big noise in an engineering concern, and to whom I mentioned your invention of an aeroplane sans propeller, as it were, and who is very interested." He's jotted a note at the top of the original letter. He says, "This letter changed the course of my life and triggered a revolution in aviation." And it did, because this letter rescued the turbojet idea in this country from oblivion.
The writer was Rolf Dudley Williams, an old friend from Cranwell. He visited Whittle at Cambridge with another former officer named Collingwood Tinling.
And they approached me with the idea of forming a company and getting on with it, and they succeeded.
A merchant bank was the catalyst.
Falcon Partners were approached by an intermediary, an engineer named Bramson. Williams Tinling got in touch with him, and he got in touch with Falcon Partners, and Falcon Partners commissioned him to write a report on the whole project, which he did, and it was wholly favourable. Bramson's report, you might say, was another of the big key points in the whole story. He'd been very much involved with aviation. He was a pretty skillful aeronautical engineer. And his report inspired Falcon Partners to go on with the job. And in March 1936, they formed the company called Power Jets Limited.
Whittle told his backers the project had a 1 in 30 chance of success. The Air Ministry quickly added another obstacle.
One clause said that I was not to work more than 6 hours a week on the job. But of course, that didn't operate as an effective control on me. I worked practically full time.
At Cambridge, Whittle also had to fit in the task for which he'd gone to university in the first place.
And I very much wanted first class honours, so I had to work like hell because I was designing the jet engine and preparing for my finals at the same time. And that was a very difficult thing to do. I succeeded in getting my first, happily, and then was able to turn back to the jet engine.
Whittle approached a manufacturer in Rugby to build the world's first jet engine. British Thomson Houston made steam turbines. Whittle drove over from Cambridge, rehearsing what he'd say to persuade the huge company to accept a contract. He succeeded, when all he could offer them was £2,000, well below what his project really needed.
The proper scientific way to go about the job would be to build a compressor and test it, build a turbine and test it, build combustion chambers and test it, and then put them all together when the results from each were satisfactory. But the cost for that would have been about £30,000, and there was no hope of getting that amount of money. So the only thing to do was go ahead with the complete engine. What we were doing was trying to prove the engine right from the word go.
In a cavernous Rugby workshop, Whittle set to work on this huge challenge.
The BTH built the engine, and I stood over it more or less while it was going on. I felt that we were going to be all right as far as the simple centrifugal compressor was concerned. I felt that the turbine was going to be all right, but I was uneasy about the combustion problem because we were aiming at 24 times the kind of combustion intensity that was obtainable in those days. But the engine became ready for running proper on April the 12th of 1937. A lot of people said it wouldn't even turn itself over. What did happen proved the very opposite. I gave a signal with my hands to raise the speed with the electric motor to 2,000 RPM, and that was done. And then I opened the main control, and it It started all right. It accelerated out of control, and so did everyone standing around it. They all went down the factory like the wind. I didn't, because I was petrified with fright. I just couldn't move. It seemed like perpetual motion, but of course it wasn't. The fact was that a pool of fuel had accumulated in the combustion chamber, which we didn't know about, and that was keeping it running after I'd switched off the control. Well, that sort of thing happened day after day. We had about 4 of that kind of runaway. Just after the engine first ran and we'd submitted a report to the Air Ministry, this was the subject of another report by Griffith, the man who turned the job down in the early days, and his report damned it with faint praise. He brought in all the difficulties, said that no propeller meant that we wouldn't have the slipstream to help us take off, and so forth.
Whittle didn't know that in Germany some people were by now far more willing to bet on his idea. One of them was Ernst Heinkel, a legend in his country's resurgent aviation industry. Von O'Hine had been introduced to him.
He was alone in his villa in Warnemünde. He explained to me that he wanted to finance the whole thing by himself if it works. And he said, I have the best aerodynamicists, I have the best designers, and I want you to tomorrow to speak with them and explain your ideas. I loved the Baltic Sea coast very much. I sure would think that would be a nice place to work, and so I choose Heinkel. Additionally, I felt I was afraid to go to engine companies. I thought they were too much ingrained in their recip engines, and my model didn't work sufficiently good.
Heinkel's company was attractive for another reason.
The whole development was very inexpensive, but when we would have asked for more money, we would have gotten it. So money was not a problem.
By contrast, the power jet's kitty was empty. As the Nazi threat grew, Whittle had a war winner, yet Britain was set to abandon it.
There were several things which hampered progress. In 1937-38, the worst was the tight financial situation. Our financial backers began to get cold feet. They had, quite unrealistically, expected that within a matter of a month or two, we would have an engine capable of flying in the stratosphere. Well, of course, we had breakdown after breakdown, and then began to lose heart. And they did not produce the money that they promised. The Air Ministry were very hesitant to help because we were in financial difficulty. After we'd first run the engine and shown that it at least was self-driving, they did agree to a very limited contract.
The ministry's grudging help only created new problems.
As soon as they gave us the contract, we came under the Official Secrets Act. That meant that we couldn't tell people what we wanted their money for. You can't go to someone and say, look, we've got a damn good idea, would you let us have some money? We can't tell you what it is, but it's very good. No, we couldn't do it.
By 1939, Britain had spent just £7,000 on Whittle's jet. His very position on the project was perilous. At the end of June, he was actually due to leave Power Jets. On his last day there, Whittle had to impress an important visitor with his engine.
On June the 30th of 1939, we managed to get a big breakthrough in the attitude of the Air Ministry, in that Pye, Director of Scientific Research, came up to see the engine run, and we managed to keep it going for about 20 minutes in his presence, and he became a complete convert. So much so that he agreed that an engine for flight should be ordered, and that an aeroplane to use it should be ordered too. When I drove him back to the station to catch his train back to London, I had the curious experience of him explain to me all the advantages of the engine, that it could run on any fuel, that it was vibrationless, etc., etc. And I just sat quietly. I was only a squadron leader at this time. I thought, yeah, you're telling me, old boy. This, of course, was the big turning point in the whole job.
The turbojet was saved for Great Britain, but Germany, unaware of Whittle's breakthrough, already had a jet plane.
I was very certain that it would work. But, of course, you always feel there's a danger, and we had made not too many pre-tests. We ran the engine before it flew perhaps several hours at the very most.
The support of a huge aircraft company had enabled Hans von Ohain to overtake Whittle. Heinkel's HE-178 was ready just days before war broke out. Test pilot Eric Varsitz was eager to take off.
He started and then he disappeared. And after a while he came back and we thought, oh, he's landing. He didn't. He made another round and we said, oh my God, he must like it. But we didn't have the airplane very filled up with gasoline. He landed and stopped the airplane just where Heinkel stood. And he said everything functioned beautiful and the engine worked well, and he was really himself, very enthused. We had a nice festival.
A jubilant Heinkel rang General Ernst Udet at the German Air Ministry.
I learned later on he called Udet and he said, hey, congratulations, but let me sleep, that's an ungodly time.
By now, Frank Whittle had been forced to move power jets from Rugby to a scruffy foundry at nearby Lutterworth. Ladywood Works was the name of the site. Today there's nothing to show that history was once made here. But in these buildings, Britain slowly expanded its jet program.
In 1939 we only had just a handful of about half a dozen. And at the beginning of 1940 we began to build up a team, and I was very careful in picking real quality. You know, first class honours Cambridge, first class honours Oxford, Imperial College of Science. We were advertising. Of course, we couldn't say what we were advertising for. And when we were interviewing them, we couldn't tell them what we wanted them for, although I think some of them guessed from the questions we asked.
Whittle's charm and enthusiasm at once inspired his new team to strive for the impossible. The noise and lack of space at Ladywood forced Whittle himself to work at Brownsover Hall, a country house nearby. Here he worked through the night, desperately aware that his work could shorten the war, and drove himself to nervous exhaustion.
My memory of him really was just somebody always working. And when he was at home, if he took any time off, say Sunday, he would sit in his chair by the fire at Broomfield, and we'd be there with his slide rule, which of course people used in those days to do their calculations, and bits of paper all over the place, working, and a little bit of time for myself and my brother, but not much, not much.
As Britain entered its most critical phase of the war, the expanding team at Ladywood was galvanised by a new order to prepare engines for a prototype jet fighter. Codenamed F-940, we know it as the Gloucester Meteor. As a potential war winner, getting it in the sky to fight the Luftwaffe now became the focus of their work at power jets. They did not know that Germany was by now developing its own twin-jet combat planes at Messerschmitt and Heinkel. The country's prototype jet, the HE-178, had not been a success, but its last flight was exploited to the full by its maker.
Heinkel invited the Air Ministry to come, and the highest who came was Udet, and somehow Heinkel used that possibility to offer a new design of a two-engine fighter aircraft. And actually, he got the contract about 2 months later.
The plane was the HE-280. The Nazis wanted it in 14 months. Heinkel passed this demanding deadline to von Ohain to build its jet engines.
Heinkel wanted things very fast. He was very optimistic, very positive, but a little bit unreal and unrealistic in his time schedules.
In Britain, the Air Ministry still wouldn't fund Frank Whittle properly, forcing power jets to work in impossible conditions.
In addition to our continuing financial problems, we had many others, like having to use the same parts over and over again when they ought to have been scrapped. And of course that was linked with the finance, because we couldn't afford new parts. We had to make do and furbish up damaged parts.
Some people continued to claim Whittle's jet wouldn't even fly. By May 1941, his engine was ready to go in Britain's first jet plane, the experimental Gloucester E-28-39. For its maiden flight, the top-secret aircraft was taken to Cranwell, where the jet story had begun. The Power Jets team followed, full of hope. On the same day, a young naval pilot, Eric Brown, was forced to land at Cranwell. Today, he's one of the few surviving witnesses of this historic occasion.
When I landed, I was a bit astonished to find so many civilians present. And when I went to check in at the mess and asked what was going on, there seemed to be almost an air of conspiracy about the whole place. And nobody would give a straight answer to this.
We'd been out the day before for some taxiing trials, and then on the May the 15th, the weather looked as though it wasn't going to work out. So I went back to Lutterworth.
That morning I went to the control tower to check if the weather was good enough for my onward flight to Croydon, but it obviously wasn't. And they said, would I mind doing a weather check for them? Anyway, I landed, and they said, would I be prepared to do a further weather test in the afternoon?
And then we got a message to say that the weather was clearing, so I rushed back to Cranwell again. And in the evening, Jerry Sayre did the flight.
An airplane was rolled out with a shape I had, well, not so much the shape, but the construction of which I'd never seen before, because it had no propeller. And an extraordinary whining noise came from it, and it taxied out to the end of the runway, and after a while eventually took off. And I was quite astonished to know what it was, because I'd never heard at this stage in my career of a jet aircraft.
The various government ministries refused to film this remarkable event. Luckily, an unknown photographer grabbed it in secret.
Jerry Sayre was sitting at the end of the runway, and a party of us was sitting just to the right, and he held it on the brakes and ran out the engine to full speed, released his brakes, and then he hopped off in about 600 yards. Quite an impressive takeoff. Then he held it down level and then glided. One of my colleagues, Pat Johnson, W.E.P. Johnson, slapped me on the back. He said, "Frank, it flies." And in the tension of the moment, I rather rudely said, "That was bloody well what it was designed to do, isn't it?"
And it landed successfully, and immediately it landed, it was absolutely inundated with people rushing out and congratulating the pilot. So I realized something quite extraordinary had taken place.
People in the area hadn't heard that particular kind of noise before, and you couldn't really hide it, however secret it was supposed to be. One officer was said to have asked another one, "How does that thing work, John?" And John replied, "Oh, it's easy, old boy, it just sucks itself along like a hoover." Another story was that someone who claimed to have been an eyewitness said there was a Merlin engine inside the hollow fuselage with a little propeller. And he'd seen it. He was a reliable witness, he claimed.
Well, everybody gravitated towards the officers' mess. And so I followed on, and there was quite a lot of hilarity going on in a corner of the room. I asked what it was all about, but still nobody would reveal what was involved. But it was quite obvious it was something quite momentous.
The flight vindicated Whittle. Britain's new jet plane was better than anybody had realised. One event particularly brought the point home.
The ministry gave us permission to open up to 17,000 just for one flight. And at that engine speed, it did 375 or 380. Anyway, it was faster than the Spitfire.
The news reached London and Winston Churchill. He ordered 1,000 Whittles. Alas, the E-28 could not be a warplane, hence the disappointment felt behind the scenes up at Cranwell.
I would have preferred it to have been the Meteor, which was then on the stocks, because that was a combat aeroplane, whereas the E-28 was just an experimental aeroplane.
Whittle's jet served notice on all piston engines, a notice that fast reached their manufacturers. They now demanded their share of a product none had invented, and which they'd rejected for years. Because of the war, Whittle would have to share his secrets with them.
All this, of course, was putting power jets into a weaker and weaker position from the commercial point of view, and that we had to swallow because it was a wartime situation. And I and several other of my team were serving officers, and we had to put national considerations before commercial considerations. That was very dominant in my mind.
Whittle played a selfless, patriotic role, in which he offered his knowledge freely to the British aviation companies. However, they were working flat out to build engines for planes like the Hurricane and the Spitfire. So in 1941, Great Britain turned to the United States, then at peace, for backup in manufacturing its jet engine. The Americans had only been told about Whittle's power plant earlier that year. Ironically, their top scientists had dismissed the concept in 1940. They concluded the gas turbine engine could hardly be considered a feasible application to airplanes. The British government expected to keep the rights in Whittle's invention, and did not intend to give it away to a future competitor. But that's inevitably what happened.
We shipped over the engine in parts in the Bombay Liberator, also with the team, who were horribly frightened lest the pilot should pull the wrong lever and they'd all drop into the Atlantic.
The company selected to build the engine was General Electric.
For America, the jet story began the night of October 4th, 1941, with the arrival of a highly secret engine assembly at a Boston airport. It was Britain's now famous Whittle turbojet, the first jet engine successfully produced and flown by the Allies.
Gentlemen, I give you the Whittle engine. Consult all you wish and arrive at any decision you please, just as long as you accept a contract to build 15 of them.
General Electric had that engine, their engine, version of the W2B, called the Type I, on test in April of 42, so just rather less than 6 months, which is astonishing. And even better than that, 6 months later the Bell Aircraft Company had their twin-engine jet flying. It was agreed that I would go over and help them out. And so I went over at the end of May. I went to Lynn under an assumed name. They insisted I use an assumed name. I called myself Whiteley. There were times when I forgot it, like in the hotel I would waking up, sign for my early morning coffee, and forget that I was supposed to be using an assumed name, and of course sign the real one. I'm told that that didn't matter really because the waiter was an FBI man.
In the Great Republic, Whittle was treated royally, and he in turn was astounded by what he found there.
It was most satisfying to see the work GE were doing because, well, they got on with the job so fast. It was remarkable, and their enthusiasm was most inspiring. And I thought at the time, if only I'd had that kind of cooperation a few years earlier, what a difference it would have made.
In America, doctors found that Whittle was by now battling with severe ill health. Back in Britain, the problems that caused it had only got worse.
The engine that was destined to be the power plant of the Meteor was a more powerful version of the experimental engine, really. There were no major difference. It looked quite similar from the outside.
The Royal Air Force eagerly awaited the Meteor, but Powerjets was not allowed to produce the engines for it. That job had been contracted to a car maker, Rover.
Glossers were getting on with the job fairly well, but Rovers were making an absolute nonsense of the engine. They just hadn't got the people who could do the job, and they thought they knew what to do. The situation became so bad that it looked as though there would be a complete hash of everything. The rovers were making such a poor job of the engine that the order for the production of the Meteor was cut right back.
Rover tried to redesign its engines and held up the Meteor by 2 years. But there was also dirty work.
We intended that the rover company should be subcontractors and only subcontractors, but unfortunately they went behind our back to the ministry and trying to get direct contracts, and eventually they succeeded in doing that. And instead of being subcontractors to us, they in effect became competitors who had the advantage of having all our information handed to them on the orders of the ministry.
In December 1942, a solution was at last found to the problems with Rover. Rolls-Royce took over the job of building Whittle's engines. But the mighty company would only weaken power jets further.
Ernest Hayes was the chief executive of Rolls-Royce. He was responsible for the Rolls-Royce part in taking over the jet development. Of course, he had come to realise that this was the future of the aero engine. And since Rolls-Royce then were one of the most prominent aero engine firms in the world, he wasn't going to be left out. I would call him an honest rogue, because when he was going to do the dirt, he told you he was in advance. And one of the things he said to me on one occasion was, he said, "We're going to be the centre of this job and nothing you can do will stop us." By 1943, the Rolls-Royce having made such a big difference to the prospects of the engine, the ministry agreed to reinstate the production of the Meteor.
With Whittle's engines, the plane finally made its first flight that year. Yet it should have been ready 2 years earlier. And had the Air Ministry pursued Whittle's idea back in 1929, a similar plane would have been available by the start of the war to repel the Luftwaffe. Lives would have been saved. The war even shortened. At least the work of Frank Whittle could now have a bearing on how that war was fought.
I thought that he was doing something quite important, because every time I asked my mother what he was doing, she used to say, "Oh, well, Daddy's doing something very hush-hush." I didn't become aware that he was anybody out of the ordinary until 1944 in January, when they made the whole thing public. And then the house became surrounded by reporters.
We had been working in complete secrecy until early January 1944, at which time, for reasons I don't really know, the British and American governments decided to make an announcement about it. It was like the world blew up around me. The shock was very considerable.
Whittle and his engine dominated the front pages.
Says here in the Daily Herald, "I knew Frank had a secret," says his wife. So the cat is out of the bag. How strange it seems to be able to talk about it. It may mean that I shall be known throughout the world. In any case, my younger son Ian is a far brighter boy than I was at his age. I think he will be a success, the success of the family.
Had you seen that before?
No, I've never seen that before. Oh dear, how wrong.
As industry reaped the rewards of Whittle's genius, new jet fighters joined the Meteor. First off the drawing board was de Havilland's brilliant Vampire. The pilots loved their new equipment, although the planes remained highly secret, as Eric Brown discovered when he came to fly them.
When I was allotted to the jet flight at Farnborough, of course it was a top secret flight, and it was in a hangar at the far side of the airfield, well away from the main activity, and there were RAF regiment guards there with guard dogs, so it was very highly guarded at the time.
Once inside, the plane was a revelation to Brown.
We're getting into the cockpit of a jet airplane for the first time. You are struck by the wonderful view, because in a tricycle undercarriage, no propeller or large engine ahead of you, it is quite remarkable. And once you start up the engine, although to listen to a jet, if you're outside the cockpit, it sounds thunderous, when you're in the cockpit, it is incredibly quiet.
Frank Whittle often visited Farnborough to check how his invention was performing.
It was quite obvious he was itching to get his hands on it and fly it. But we were always alerted that he was coming, and a little memo would be passed round saying, would you make sure that the 2839 was not serviceable for flight on that particular day. And because this would stave off Frank, it was obvious they didn't want this wonderful airplane and this wonderful man to be united in case there was an accident. So he twigged this pretty soon, and I think he played along with it.
In July 1944, the Gloucester Meteor became the first jet fighter to enter operational service, when the Air Force allocated its initial supply of planes to 616 Squadron at Manston in Kent. By now, the Luftwaffe could no longer mount air raids over Britain, but these Meteors were quickly put to work, intercepting a lethal new menace, the V-1 guided missile. Germany's flying bomb terrified the Londoners who were its target. In the skies over Kent, the Meteor pilots sought to prevent V-1s reaching the capital. Some used their wingtips to flip the missile over, so it crashed. Around this time, Allied pilots were startled to find themselves being attacked by a German plane with no propeller. This was the Messerschmitt 262. Germany's own jet program had by now advanced to this sophisticated design. It had been chosen instead of the HE-280. The Nazis never liked Heinkel and had cancelled his promising jet fighter. Yet it could have been mass-produced by 1944. By contrast, the 262 arrived late and was rushed into battle too soon. In Britain, meanwhile, Frank Whittle seemed at his peak. He was a national hero, while his company now had a custom-built factory from which to expand. He had a clear vision for its future.
I always wanted to include manufacturing in our duties. In 1944, power jets had reached the point where they were able to produce, say, batches of 40 or 50 engines. And we had a first-class nucleus for proper manufacturing organisation.
Power jets also had some outstanding work in progress. Whittle was already planning the second generation of jet engines.
There was the LR1 turbofan, which would have been the first turbofan in the world. There was the engine for the Miles M52, the supersonic aeroplane. Those were our two big projects which we had in hand.
LR1 stood for Long Range 1. Whittle saw the scope for jets that would fly planes further as well as faster than pistons. But he would need a more efficient engine.
From the earliest days of the turbojet engine, I was bothered by the fact that it has a basically low propulsive efficiency, about 50% as compared with, say, a propeller at moderate speeds of 80%. And so the answer to me was that we must gear down the jet in some way. And that led to the concept of the turbofan, for which I took out a patent in 1936.
The turbofan is a turbojet to which a fan has been added. This fan causes air both to flow through the core of the engine and to bypass it. This additional jet of cold air increases thrust and improves fuel economy. The design had huge potential.
With a turbofan you can expect propulsive efficiencies of 75% or even better if you have a very large bypass ratio.
As piston engine bombers approached their design limits with planes like the Lancaster, Whittle saw a timely use for his new bypass jet.
As the war progressed, in 1943 for example, I came to the conclusion that it could be the answer to a long-range bomber for the Pacific War. We also visualised it as an engine for a transatlantic aeroplane.
Whittle was already predicting long-range jet airliners and the kind of engines they would need. But it was the other power jet project that would grab people's attention.
The engine for the supersonic plane, the M52, was an aft fan with afterburning, all tacked onto the back end of the W2700 jet engine, and that should have given sufficient power for the Miles M52 to do 1,000 miles an hour. I think it would have done it.
Despite its huge potential, Whitehall never felt comfortable with power jets. It was a private company, but its driving force was a serving officer, and it was publicly funded. The fault lines were clear.
I realised that there was a complete mess from the contractual point of view. There were no effective agreements, and no one except Power Jets had risked any money, except the government, of course. And I felt that the government, having put in $2 million, that all the companies should be nationalised, forming a collective turbojet establishment. And of course, I hoped that Power Jets would be at the top of the pyramid, with myself as chief engineer.
Whittle's proposal was considered in the high levels of government.
Sir Stafford Cripps, the Minister of Aircraft Production at that time, used what I'd said to get the ministry out of the mess that they'd created by nationalising Power Jets only, which relieved them of all their undertakings.
It was expected that Power Jets would still continue with its advanced engine projects.
But then other firms began to create difficulties. They said they weren't going to have the government competing with private enterprise. So considerable pressure was brought to bear on the ministry.
And the minister caved in to the large aero-engine companies.
So we, the people who had pioneered the whole thing, were deprived of the right to design and build engines. Sorry. That was too much for myself and my leading team members, and most of us resigned.
The supersonic plane and the turbofan project had by then been cancelled. The civil servants found a reason to justify this loss.
Believe it or not, the minister said that people wouldn't want to fly at speeds more than about 250 miles an hour.
As Whittle left Power Jets, he was acutely aware of the commercial opportunity that was now at stake.
The position in 1945 and 1950 was that Britain was really ahead of the world in all forms of gas turbine development, but stupidly we allowed the lead to slip away.
In 1945, the Allies discovered the Germans' impressive range of jet planes and their designers.
After the capitulation of Germany, I was at that time in Farnborough the CEO of the captured enemy aircraft flight. So I was sent to Germany and to look at their advanced aircraft, and also at the same time to interrogate their designers and test pilots. Amongst them was von Ohain, and naturally I wanted to know what his connection with the Whittle patent had been in Germany. But he was not going to answer this question. He was very non-committal and sidestepped it as much as he could.
Brown flew the various German jet planes, including the Messerschmitt 262. The Allies already knew that its engine, the Umo 004, was a sophisticated axial flow design. Now they could compare its performance with that of the less complex British jets.
So a more efficient engine in many ways. It was highly unreliable. The Umo 004 in operational service had a scrap life of only 25 hours. And the engine, when I flew this engine, I found it extremely sensitive and difficult to handle because it did not like quick throttle movements, either accelerating or decelerating. Any quick throttle movement either way could possibly cause a flame out of the engine.
Whittle's jets were more reliable, but he could take them no further. The course of events brought anguish.
I think my mother was most distressed by what was happening to father. She was most distressed. I could remember her crying about it at times, because she would tell me, "Oh, Daddy's so unwell because of what's happening, and it is such a shame, and how can they treat him like this?" Yes, it's very sad for her. He managed to soldier on in the RAF. He was an Air Commodore in 1946, but in the end, by 1948, he'd been declared as unfit for flying, and somehow that was the last straw, and he he and the RAF both agreed that he should retire, and he did.
It's been very sad for him.
Oh, very sad, yes. The Air Force was everything to him.
The public knew none of this and saw a war hero receiving his just rewards. In 1948, Whittle went to Buckingham Palace to collect a knighthood. He also had a financial award for his invention, which was good for the time. Worth nearly £3 million today, it would soon become clear he was greatly under-rewarded. He sought a role, but his stature made him hard to place in an industry he himself had founded. No engine maker hired his services.
In many ways, I paid quite heavily for the work I did. There was the awful race against time. That dominated life. On top of all the technical difficulties, there were the financial difficulties, there was the skullduggery of people who were messing things up, and it was frustration after frustration, and it took its toll. I began to have a series of nervous breakdowns, and for years, it was years before I really recovered my health.
Britain stole a march on the rest of the world when it launched the first jet airliner. The beautiful new plane, with its 4 engines, was a fruition of all Frank Whittle's early visions.
First, after he left the RAF, he turned his mind to the introduction of the Comet, and he joined BOAC as a consultant to help them introduce the Comet into service. He was very worried at the time that the thing was being rushed into service. I've got his 1949 diary where he discusses the strength of the square windows, and he was worried about that at the time, and was making a suggestion to de Havilland's on how they could get over the problem.
Whittle's advice was ignored. The Comet crashes which followed were caused in part by its square windows. With time on his hands, Whittle travelled and tried to recover his health. He also turned to writing his memoirs. The jet age took off without Frank Whittle, but the Royal Air Force was soon re-equipped with the benefits of his invention. By 1950, the Gloucester Meteor provided the backbone of Britain's air defence capability. It was a fitting outcome to all the secret toil of the Power Jets team in the dark days of the war. The nation did at last build its own supersonic fighter, in the shape of the English Electric Lightning, while jet engines also powered an awesome British fleet of nuclear bombers. But the country could never really afford such planes. They would later play an important role in the Falklands campaign, but were destined to become museum pieces. British civil jet planes fared little better. After the Comet crashes, it was Boeing's 707 which brought long-range jet travel to the masses. By 1960, airlines were mostly buying their planes from America. That year, the bypass engine entered service. Turbofans soon followed. With their far better fuel economy, they were just what the airlines needed to realise low-cost global travel. For Frank Whittle, it was the ultimate vindication of his wartime vision, and revealed the sheer folly of cancelling his pioneer turbofan. Yet he never worked on jet engines again, and memories began to fade of how the story had begun.
I think in this country they were beginning to forget all about Frank Whittle by the 60s and 70s.
It was all so different in the United States.
They were so much more gung-ho. They were very good at slapping him on the back and telling him what a good chap he was.
In 1976, Whittle went to live in America.
I think he felt more recognised over in the States than he did over here.
After the war, Hans von Ohain had himself moved to America to work on jet propulsion for the US Air Force. Fascinated by each other's work, Whittle and von Ohain became good friends. Back across the Atlantic, Britain eventually rediscovered its genius of the jet.
By 1986, even the Queen took a hand and ordered him the Order of Merit, and other honours came along following that. So I would say from about the early 80s onwards, people began to remember who it was who was the prime pioneer of the turbojet.
And also a man with a profound legacy. Today, we make almost 1.5 billion air passenger journeys a year, cheaply and safely, thanks to Frank Whittle. He shrank the world, but his gift to Britain is less appreciated. Its famous plane makers have departed, but today, Rolls-Royce is a world leader in building jet engines.
I'm often asked how I feel about it, and it's a question I find very difficult to answer. Things could have been a lot better. We could have had a much bigger influence in the war than happened. But when I see what's happened in the way of civil aviation and military aviation too, but particularly civil aviation, I can only say it's extremely satisfying, especially when you see something like the Concorde. And one of the things you see I never foresaw when I was working on this thing is that I would be a passenger crossing the Atlantic in 3.5 hours. And incidentally, another thing I didn't foresee is that I would have a son who would be flying 747s as a captain in Cathay Pacific.
Kai Tak Aerodrome at Hong Kong had a very interesting approach, a curved right-hand turn right down to almost a touchdown. And when Father came with me in the back of in the cockpit in a Boeing 747, he was very startled when he saw that his son was flying an airplane at 1,000 feet straight towards the foothills and then making a steep final turn, which of course was quite normal at Kai Tak. It was the way you had to do it. I hadn't briefed him, unfortunately, so he was very white-knuckled by the time we landed. He was continuing to theorize in aerodynamic improvements and aero-engine improvements until the end of his life. He always took an active interest in Concorde and looking into a second-generation SST, supersonic transport, and making recommendations and speaking publicly and privately amongst the industry to try and encourage the airframe manufacturers to take the risk and embark on another generation of supersonic transports.
Concorde is a marvellous aeroplane. I've flown it many times, but I'm looking forward to the next generation of supersonic transports, which I think should be capable of carrying 300 passengers for distances of the order of 4,500 miles, like San Francisco, Tokyo, at speeds of about a Mach number of about 2.3. That's we're getting up to 2,000 miles an hour, as compared with the Concorde's 1,350. But beyond that, I think we're going to see even much higher speeds than that in due course. Unfortunately, they're going to be very expensive propositions.
Sir Frank Whittle died in August 1996, assured of his position as the greatest aero engineer of the 20th century. The Royal Air Force paid fitting tribute to its distinguished son with a memorial service at Westminster Abbey.
He and I had wanted the opportunity to fly together, preferably in an open cockpit biplane, so that together we could loop and spin and climb and dive. This modest ambition was never realized for one reason or another. The nearest we got was when I flew him to Hong Kong in a Boeing 747. On the last morning of his life, I leant over his bed and said, "Dad, let's put on our kit and go flying." He opened his eyes and looked at me and smiled. That evening, with Hazel holding his hand, he died. And I wondered if he went flying, and if he did, if he went on his own, or did he have a companion? He was cremated in the USA, and the air attaché there brought his ashes over to this country, and I went to Heathrow to meet the airplane, and I came home and put the ashes on the bookshelf in my study with the ashes of my mother, who died 3 weeks earlier. I decided to put them in at the Church of Cranwell, and they organised a meteor and a vampire. So we flew the ashes up to Cranwell, and they were interred there with a little ceremony.
October 4th, 1941. Incredible as it may seem, these crates marked the start of the development of the first jet engine in America. They contained an experimental engine which was flown to the United States from Great Britain under great secrecy in the fall of 1941. This flight was the direct result of a conference in the Washington office of General Arnold a few weeks earlier. Here was the actual beginning of the jet story in America.
Gentlemen, I give you the Whittle engine. Consult all you wish. Arrive at any decision you please, just as long as General Electric accepts a contract to build 15 of them.
These were the plans of the first turbojet engine that had been successfully produced by any of the Allies. They were the results of a long, hard struggle by England's group captain, Frank Whittle. He had worked toward jet propulsion in the face of many difficulties, and he had succeeded. The Air Corps felt that jet propulsion had tremendous possibilities, and the British Air Ministry made all their information available to the United States. The men of General Electric knew from their with the National Advisory Committee for Aeronautics that the essentials of a turbojet were a compressor and a turbine.
I cannot overemphasize the secrecy and the importance of this work. We know that both the Italians and the Germans are working on jets. I hardly need tell you that they must not win the race.
General, given unlimited priority, we will have the first unit running on test in 6 months.
6 unbelievably short months in all to plan, design, and build the first American jet engine for a revolutionary new principle of flight. Yet these men were able to make this promise to their government in time of war because actually this problem was not new to them. It really began on the campus of Cornell University in 1903, where a young mechanical engineer named Sanford Moss was working for his PhD. He was engaged in research for his thesis on gas turbines. He and his work had been consigned to this little building because there seemed to be a certain amount of noise connected with it. Not to mention smoke and odd smells. When he had completed his work at Cornell and received his degree, Moss went to General Electric, where he joined other experts and continued his work. Later, they set up a research department to study turbines of all kinds, as well as compressors, pumps, boilers, and related equipment. By 1918, Moss and his fellow workers had accumulated a tremendous amount of knowledge in relation to turbines and compressors, and as a result, he was called to Washington. There, the National Advisory Committee for Aeronautics initiated work with Dr. Moss on a practical turbo supercharger, which the Air Corps hoped would increase the altitude performance of its World War I fighters. A gasoline engine runs on a mixture of air and fuel which burns in a cylinder. At higher altitudes, the atmosphere becomes progressively thinner so that the engine cannot get enough air to burn as much gasoline as it should for maximum power. The turbo supercharger simply adds a compressor to the engine, which packs or charges the thin air into the cylinders. This allows the engine to burn more fuel and deliver full power. The compressor is run by a turbine, which is turned by the exhaust gases of the engine. Moss's work on the turbo continued, and his improvements had a tremendous influence on aviation. In 1920, the Army established a world altitude record of 36,000 feet, proving the turbo in air so rarefied that the pilot became unconscious and fell almost 6 miles before pulling out. General Billy Mitchell's famous test, which demonstrated for the first time the tremendous importance of air power, was actually made possible by Moss's turbos. Mitchell's plane had to come in at 15,000 feet in order to avoid theoretical anti-aircraft fire. To give a plane enough power to carry a 2,000-pound bomb at that altitude, Mitchell had General Electric turbos installed on new twin-engine Martin bombers, and the results made aviation history. With the beginning of World War II, the Air Force's interest in turbos was greatly intensified. They quickly became standard equipment on such outstanding aircraft as Republic's Thunderbolt, Lockheed's Lightning, Consolidated's Liberator, and old reliable, the Boeing Flying Fortress. The high-altitude daylight strategic bombing operations which destroyed the strength of our enemy in Europe would not have been possible without turbos. They have contributed immeasurably to the science of flight and continue to do so. They are used on some of today's finest piston engine planes. The most formidable weapon the world has ever seen was carried by a turbo supercharged plane. So in 1941, with a new but related problem, it was only natural for the Air Corps to again turn to the same organization and ask them to build the first American turbojet. And build it they did. At a series of secret meetings 1 month before the arrival of the Whittle engine, the project had been started with a small nucleus of key personnel. These men picked those they wanted to work with. However, in most cases, they did not let them know what they were to work on. There were over 1,000 men on the project, but less than 100 actually knew what they were making. Planning and assembly of the engine itself was segregated in an entirely separate building and heavily guarded 24 hours a day. Many of the parts were made in the regular supercharger department, but as a further protection, the project was called a new type of turbo and simply given another production number, Type I. All the vast resources of the company were thrown behind the project. The knowledge gained in years of production and design of giant turbines of every kind. The research laboratory for special metals. The experience gained in the manufacture and operation of thousands of turbo superchargers. And the vast store of knowledge of the consulting laboratories. During the actual design and manufacture under D.F. Warner, these great resources led to the modification and improvement of the Whittle engine. For example, the English had trouble with turbine bucket forgings because of the high temperatures involved. But it was an old story to these men, and their long experience with turbos hastened the solution to this problem. Also, the English impellers had been giving trouble because of cracking, but skilled craftsmen were already making hundreds of thousands of successful impellers for all types of superchargers. American techniques of rotor balancing were very advanced and contributed greatly to smoothness of operation. Yet in spite of the diversity and size of the operation, there was not a single failure in security. Today we realize even more fully than the pioneers the almost incalculable importance of that first American jet engine, the forerunner of the engines that power the military planes of today. Yet those early workers seemed to sense the true value of their work, and it brought them together. There was a wonderful spirit of common purpose, of cooperation between the people who did the work, Britain, our Air Force, and the men of General Electric. In this atmosphere, the engine grew at an unbelievable rate, until at last the first engine, right on schedule, rolled under heavy guard into the test cell. Now they would see the results of 6 months of round-the-clock effort. But they would see much more than that. They would see the birth of the jet engine in America. They would see the first really radical change in air power since the Wright brothers' flight so many years ago. They would see the first faint beginning of a whole new era in the age of flight. That is, they would see it if the engine ran. Was to see it fly. Meanwhile, under the same rigid secrecy, the Bell Aircraft Corporation had been designing, laying out and building the Air Comet to be powered by the new engine. They too had performed miracles of production in a startling new field.
I can't get used to working on a plane without a propeller.
Neither can I. I hope it flies.
There were a lot of other people who hoped it would fly too, from top brass to Joe Average Man walking along Main Street, USA. Of course, he wouldn't hear about this particular plane for 2 or 3 years, maybe never. But he's a guy who carries deep within him a hope and conviction that any plane America builds will fly. These are the original films of the first jet plane ever to fly in America. That first flight on October 1st, 1942, less than a year from the start of the project, jet-propelled flight in America became a reality. They had gotten off to a flying start, but in a race, it's the stamina that counts. So everybody kept right on working. The original engine, the IA, delivered 1,400 pounds of thrust. It was soon followed by another engine with more power, the I-16 with 1,600 pounds of thrust. Then came the J-33 with 4,000 pounds of thrust, and the jet engine really came into its own. The first flight of the J-33 was in June of 1944 in a Lockheed F-80 Shooting Star, again less than a year from the start of the project. This outstanding plane set many records, such as coast to coast in 4.5 hours, and became our first operational jet fighter. In order to get the jet industry moving and in the interest of national defense, GE passed along its plans to other manufacturers. Allison began mass production of the J-33 engine to help meet production requirements of the F-80 Shooting Star. The British Whittle engine and the first engines designed by GE used compressors of the centrifugal type. In these, air enters the hub and is hurled radially outward. However, even prior to seeing the British engine, work on an axial compressor had been started with the National Advisory Committee for Aeronautics. In this compressor, air flows in a straight line to the rear. The axial compressor increases the engine's efficiency and handles a greater volume of air without increasing the engine's diameter. Long-range research led to an axial flow J-35, which powered the Republic Thunderbolt. and the Douglas Skystreak, holder at that time of the world's official speed record of 640 miles per hour. 8 of these powerful new jet engines were also used in Northrop's 100-ton Flying Wing and many other planes in the rapidly developing jet field. During these years of progress with land-based aircraft, the Navy had worked with the McDonnell Aircraft Corporation and Westinghouse to develop the Phantom. Proof that problems associated with carrier-based aircraft were not beyond solution came with the Phantom's first takeoff and landing from an aircraft carrier. Meanwhile, a school was established at General Electric to train the people who would install, operate, and service their new GE jet engines. One of the courses given is simply a general familiarization with the principles of jet propulsion and the jet engine.
Ever since man undertook the conquest of the air, he has had 2 primary considerations. First, the aircraft itself, and second, its method of propulsion. Needless to say, he has not always been successful. Sometimes the airframe itself has been unsatisfactory. At other times, the method of propulsion has lacked the necessary power. In this case, for example, it's extremely simple. While in this, it's so complex that it borders on confusion. Actually, the early attempts at propulsion by reaction were not associated with aircraft. And, as in the case of most of man's early endeavors, they led to some rather startling results. The principle itself is very simple. Newton's third law of motion states that for every action, there is an equal and opposite reaction. For example, an ordinary rotary lawn sprinkler turns because of the reaction of the arm to the action of the jet of water. It does not turn because the water squirted out pushes against the air. It would spin just as well in a vacuum. Similarly, the jet plane flies because of the reaction to the jet. It does not fly because the jet pushes against the air behind it. The engine itself consists of 2 main rotating elements, the compressor and the turbine, which are both mounted on a single rotating shaft. Air is drawn in, compressed, and packed into the firing chambers where fuel is injected. The constantly burning fuel tremendously increases the energy of the enclosed gases, which rush through the turbine and out of the tail cone. The turbine, operating like a windmill, supplies the power to spin the compressor. The expanding gases pushing their way out of the rear at about 1,200 miles per hour give the plane its forward thrust.
This, then, is the simple principle of propulsion which changed the whole outlook of the aviation industry. By 1951, GE's production models were delivering more than 5,800 pounds of thrust, a 5-fold increase in 10 years. These engines are being mass-produced at both Lynn, Massachusetts and the great new Lockland, Ohio plant, the jet center of the world. Lockland represents more than huge production facilities. It represents a new production plan. Thousands of suppliers and subcontractors contribute to the manufacture of the jet engines, which are assembled at Lockland. Thus, all sources of supply, down to the smallest individually owned machine shops, are benefited by the program and kept mobilized for production. The Lockland plan is truly another milestone. Just as the engines which roll from its production lines are the end product of many milestones, the result of almost 50 years of the best thought and effort of executives, engineers, scientists, and skilled craftsmen doing the work they are best fitted for in their own way. This freedom of effort is, after all, the real heritage of all Americans, and the engines are living up to that heritage. Today, General Electric turbojets are doing their job powering the great new planes they were designed for. Such planes as the Republic XF-91, high-speed, high-altitude interceptor, the North American F-86D, the Martin XB-51 superfast tactical bomber, the North American Sabre, holder of the world's official speed record of 671 miles per hour and the 100-kilometer closed course of 635 miles per hour. The North American B-45 Tornado, the first operational jet bomber. The Boeing B-47 Stratojet bomber, which in 1949 flew non-stop coast to coast in 3 hours and 46 minutes. and the mighty Convair B-36, the intercontinental bomber, which is powered by 6 turbo-supercharged piston engines and 4 jets. These and others are the planes which must maintain the common security of the free peoples of the world and thereby ensure peace. In one 6-month period, 3 new GE engine designs were okayed for production, each powerful than the preceding one. The last of these is no larger than the model then in mass production, yet it delivers so much more thrust that it is not even in the same class. Even so, by the time any new engine is in mass production, still newer and better engines are on the way. Engines that will be a tribute to the life work of Dr. Moss, who died in 1946, 1 year after being awarded the Collier Trophy, aviation's highest award. Moss's work is finished, but there will always be others to carry on with new ideas. Perhaps we will travel from coast to coast in 3 or 4 hours of quiet, vibrationless comfort. Certainly our energetic and progressive aircraft industry will give us commercial jetliners as soon as the time is right. Even the atom may release its giant strength for aircraft. The Atomic Energy Commission, the Air Force, and General Electric are already cooperating on an atomic power plant for an aircraft to be built by Convair. NACA, the U.S. Navy's Bureau of Aeronautics, and a number of private corporations are also making real contributions to this program. Developmental engineering moves forward with great new facilities such as GE's Aircraft Gas Turbine Laboratory. Here engineers can simulate conditions for tomorrow's aircraft. Here men look ahead at the requirements of the planes of the future, requirements established by the product planners of the engine builders, of the airframe builders, and of the aircraft users. These are the molders of aviation progress. As long as imagination, research, design, test, and mass production continue year after year in a never-ending, constantly improving chain, there is no limit to the future of the aircraft engine. And so the jet story grows. In 10 years, we have come from this to this. No one can foretell the tremendous strides the aircraft industry will make in the next 10 years. Yet we can be sure that the engines will keep pace. The engines that are keeping and will always keep America strong.
How indifferent we've become. We've forgotten what it is to be astonished. Another new plane, one more, so what? But there is something unusual about it. It's long and has a sharp snout, and its head is lowered. There haven't been any like this before. And it has a delta wing folded back to the tail. The wing's leading edge is razor sharp. A powerful 4-engine unit is mounted below. And there's another singularity. It has no stabilizer. This is the new Tupolev supersonic airliner. Take off. Script, Anatoly Agranovsky. Direction, Vermisheva. Director of Photography, Khavshin.
a Central Documentary Film Studios production. Andrei Tupolev, now in his 80s, possesses talent and insight to such a degree as to become a living legend. This film is about the Tu-144, his latest model in a long life wholly dedicated to aircraft engineering. When it was conceived several years ago, there were few, even among the top rankers, who believed in its practical realization. They would often get together like this and calculate, design, ponder, and discuss indefinitely.
Процент на 40 уменьшить относительно толщину крыла.
А что мы можем ждать от этого утончения по качеству самолета? Чего 0,2?
Качество, да, максимального качества. Сколько процентов? Сколько процентов? Это порядка 3%.
They had worked together for years and understood one another at a glance. It's said locally that anyone who can out-argue the general designer can count on a bonus or a promotion. Couldn't a flutter effect appear in your control system? And the body-strengthening engineers will see how much metal they must add. I'll do the drawings counting on the body-strengthening engineers making their corrections. Get started, and we'll find some time later for a report back. That will help us arrive at the overall final form. We discussed that question 2 days ago. It's clear now. You finished turning over the finals to Ilyushin so he can speed up his part of the job.
Окончательные материалы для того, чтобы он мог быстро исправить свою работу.
The model was tested at supersonic speed. And here the character of the streamlining was studied. The Tu-144 required 10 times more investigation in the Great Wind Tunnel than any previous aircraft. This is father and son. Andrei Tupolev has trained hundreds of aircraft designers. He founded a school of aircraft engineering. His son Alexei, chief designer of the Tu-144, has followed in his footsteps. A tailless design was chosen. What would it look like in reality? The Tu-144 would have been inconceivable without metallurgists, chemists, instrument makers, and electronic experts taking an active part in its development. New alloys and new kinds of ruled metal were needed. The electronic equipment accounts for half the plane's cost. Some 10,000 parts are made of plastics, so the building of this plane was a common achievement of Soviet science and technology. This is a fighter plane. It flies at the design speed for the Tu-144, 2,500 kilometers an hour, more than twice the speed of sound. So it's nothing new. Our foremost Army pilots have mastered it. What is new, though, is that Tupolev has put this incredible speed at the disposal of ordinary mortals. However, not only the speed, altitude, and distance barriers have been surmounted, but the reliability barrier, too. The landing gear was being tested. What was there about it that instilled confidence? Should the hydraulic system suddenly fail, another backup system would take over, and then, if necessary, a second backup system, and even a third. So one failure is nothing to worry about, and even two failures will not cause a crash. The crew had been pre-selected and had rehearsed the flight over and over again on the ground. Airborne, they wouldn't have the time to recall, waver, or grope. They'd have to make split-second decisions, and that meant they had to know the plane like themselves. Each of them had a college education and lengthy, thorough training for the maiden flight. Commander Yelyan, give us a readiness report, please. First, we'll make the landing gear retraction and release test. I wanted to hear what you have to say about takeoff. We've considered Alexei's remarks about reducing the ground run. The shorter the takeoff, the quicker will be airborne. Well, to you who are about to fly, fingers crossed. The maiden flight took place on December the 31st, 1968. Everything had long been in readiness. They'd been waiting for clear skies, but the weather continued foul, and nerves were wearing thin from the strain. Finally, however, the very last day of the year dawned clear. The mercury fell, and visibility rose. Andrei Tupolev had watched 120 maiden flights, and here he was again, waiting. Meet Flight Commander Edward Yelyan, Engineer Yuri Zeliverstov, Leading Test Engineer Vladimir Benderov, and Second Pilot Mikhail Kozlov. Yes, it was a fine day indeed. It was good to be alive on a day like that, as a well-known test pilot put it. This is Dolphin 1 ready to take off. Permission granted. Got you. Some compare it to a bird, for a bird never takes wing with its head drawn back. The plane took off and gained altitude. There was nothing left for us to do but watch and wait. Nothing depended any longer even upon the general designer. Mr. Tupolev, how did you begin? I matriculated at Moscow's higher technical school because I had a bent for engineering. Our lecturer on aviation was Nikolai Zhukovsky. We built the first glider, and I made my first flight. When Zhukovsky decided to set up an aerodynamic laboratory at the school, he said that Tupolev had clever hands, so he would be in charge of the equipment. Actually, there wasn't any laboratory at all, simply a big hall the school allotted us, and that's how it all began.
Когда же пришла революция, то мы, около Николая Егоровича Жуковского, был уже тесный кружок людей, которые, приходя к нему...
When Soviet power came, Nikolai Zhukovsky had gathered a close circle of people dedicated to aviation.
И мы хотели всей группой вместе...
We all wanted to help our Soviet country.
Нашей уже советской России.
Tupolev has advanced through nearly every stage of aviation. He even recalls planes of plywood. He built the first all-metal aircraft. This is one of them, the ANT-3. ANT are his initials. And another, the Maxim Gorky, at that time the world's biggest. And this is the ANT-6 at the North Pole. The famous ANT-25's non-stop flights won world acclaim. It took Chkalov 63 hours to fly non-stop from Moscow to the United States.
For more than 30 years, it was a plane that captured the imagination of the entire world. From Africa to South America, from Asia to Europe, from London to New York City, the aircraft simply known as Concorde galvanized the globe. Its sleek aerodynamic structure and supersonic speed brought passengers to a whole new level in transportation. In Britain and France, the plane became a symbol of national pride. During the Cold War, where every technological breakthrough seemed to come from either America or the Soviet Union, the Concorde proved that Europe still mattered. And while this supersonic transport became synonymous with patriotism, it's also remembered as a plane that turned into an economic disaster. With skyrocketing development costs and a hefty price tag for admission, when it finally debuted, only the rich and powerful were able to fly the Concorde. And in an era of heightened environmental awareness, the aircraft was denied the most lucrative routes across the Atlantic Ocean. If not for the endless sums of government money, it may have never seen the light of day. In the end, the plane was a two-edged sword. Hated by the economists, yet loved by the people, Concorde, after nearly 3 decades in service, became one of the most recognizable aircraft in the world. During a time when faster meant better, it soared over its competition, symbolizing the absolute best in European engineering and aerodynamics. On October the 14th, 1947, aviation enters a new and uncertain era. when Bell's rocket-powered X-1, launched from a B-29 Superfortress, becomes the first aircraft to break the sound barrier, flying at over 800 miles per hour at Mach 1.06. This breakthrough, along with the introduction of jet technology, causes countries to pour enormous resources into finding ways to go faster and faster. During the Cold War, with both America and the Soviet Union possessing the atomic bomb, the requirement that airplanes go supersonic is a must. This leads to a revolution in aeronautical design. Straight-winged aircraft, unable to achieve faster speeds, are replaced by swept-wing planes, most noticeably during the Korean conflict, as American F-86 Sabres battle Soviet Union MiG-15s. Bombers like the B-29 and the B-36 Peacemaker evolve into the swept-wing B-47 Stratojet and the B-52 Stratofortress. With the two superpowers investing gigantic sums of money into aircraft design, the nations of Britain and France are forced to play catch-up. In England, where the Gloucester Meteor symbolised London's place at the vanguard of aviation technology, during the Cold War, a trifecta of planes known as the V-bombers are unveiled as a deterrent force against the Soviet Union. The third in this trilogy, Avro's Vulcan, a supersonic bomber equipped with 4 turbojets, incorporates a new delta-wing design, giving the aircraft increased speed over the swept wing. Across the English Channel, where aviation was born, the nation of France also experiments with supersonic aircraft. Dassault's Mirage 3, a plane incorporating the delta wing design, flies at over Mach 2.2 in 1958. In addition, the Durandal is also tested during this time as an experimental supersonic plane. But despite their respective legacies of being at the forefront of aviation technology, after the Second World War, with both England and France's economies shattered, it appears their best days are behind them. In the realm of military aircraft, there seems to be no way to compete with the vast resources of the United States. However, there is one area where, if England and France pool together their resources, a formidable challenge can be issued against America and the Soviets. This comes in the form of a proposed supersonic transport airliner.
Mr. de Gaulle was president of France at the time, and French prestige was sort of important. The French were very, very concerned, as were the British and other Europeans, about the loss of technology prowess in the aviation industry. There was a feeling in Europe at that time that the Concorde project could be a vehicle, a catalyst to jumpstart the European aviation industry after decline.
With only military planes capable of breaking the sound barrier, there's much talk about having this technology cross over into the civilian transport market. With jets replacing propeller-driven aircraft as the preferred mode of flying, conventional wisdom leads many to speculate that the next logical step for passenger travel is the ability to fly faster than the speed of sound. In America, the undisputed champion of aircraft design, it appears inevitable that they will build an SST. The Soviets, not wanting to be outdone by their rivals, are no doubt going to follow suit.
This took place during the height of the Cold War. The Cold War was taking place. You have to remember there was competition in the aerospace defense. We had announced the Apollo program at the end of 1961, which was in effect a Cold War program.
I think that the attraction of the supersonic airplane was like the attraction of much of the space age prestige, the national honor that you had to be. If you didn't demonstrate that you could do this, you weren't in the front ranks.
This leaves the powers of Europe with an important decision to make. Will they build their own SST and compete on an international scale? The answer is given on November the 28th, 1962, when representatives from the English and French governments sign a treaty creating a powerful new consortium between the British Aircraft Corporation and Sud Aviation.
Airliner of the future. This is a model of a supersonic jet which Britain and France hope will dominate transatlantic travel. Flying at twice the speed of sound, it will hop the ocean in 3 hours. Representatives of the two countries sign an agreement to share the $300 million cost and hope to have the plane operational by 1968. The delta-wing craft will carry 100 passengers and cruise at 1,400 miles an hour. Engineers say it can use present runways and fly so high there will be no sonic shock when it breaks the sound barrier. The world grows smaller.
The two companies agree to build a supersonic transport with no cancellation clause, causing numerous airlines to immediately place orders, including America's Pan Am Airways.
Pan American will announce it has ordered 6 new Concorde supersonic jet transport, which can fly from the United States in 2.5 hours. You can tell him he's given me the best argument for not having one airline represent the United States that I've ever heard. And I'm going to spend the next time I'm here really giving a screwing to Pan American, because that sticks it right to us. How can we possibly go ahead now with our program, to which we're going to spend an awful lot of money, which was very important to the United States, which affected the balance of payments in hundreds of millions of dollars, and I'm going to put all this out and then go ahead about 24 hours before we're about to make our announcement.
Across the Atlantic Ocean, this treaty causes President Kennedy to act swiftly. And in June of 1963, at the Air Force Academy's graduation, he announces the United States' own SST program.
30,000 spectators packed the stadium at the Air Force Academy in Colorado Springs for ceremonies that will graduate cadets into officer ranks. They hear President Kennedy call for a partnership of government and business to develop a supersonic passenger plane to hold the U.S. lead in commercial aviation.
He had been under some pressure to announce this project. Vice President Johnson formed a little committee to look at the SST in the spring of that year, and he recommended vigorously that we go ahead with an SST. The Anglo-French had announced the Concorde project in '62, and that also created pressure for Kennedy to do something. There was also some pressure from the aerospace industry people to respond to what was taking place both in Britain and France and also Russia, which had its own SST program.
In the Soviet Union, work begins on their supersonic Tupolev Tu-144, with each plane now in a race to the finish line. Beginning in 1965, 2 prototypes are built, known as 001 in Toulouse and 002 in Bristol. Luckily for Britain, its aerospace industry has a huge jump on the competition, having built numerous experimental aircraft proving vital in the research and development of the Concorde. The Bristol 221, incorporating a variation of the Delta design known as the OG wing, is tested in order to determine the SST's range and payload. The TSR-2 bomber, an airplane cancelled due to the budget cuts of the 1950s, provides invaluable information about the Concorde's most daunting obstacle, its power plants. Using Bristol's Olympus engines, the TSR-2's testing sheds new light on the challenges supersonic planes face in the air. In the laboratories of the British Aircraft Corporation and Sud Aviation, rigorous examinations are carried out, investigating hundreds of materials and the effect heating has on them.
Building the Concorde required new materials, and they had concerns about heating, which had never been a sustained problem. You had people that had encountered heating in certain instances in brief encounters with supersonic flight, but if you're going to cruise at supersonic flight, then you've got a totally different heat dissipation problem.
For a period of 18 months straight, round-the-clock, 24-hour trials are conducted. At its peak, over 600 subcontractors are brought into work on the Concorde, employing over 200,000 people.
Filton, Concorde 002 stands like a great bird in a massive cage at the British Aircraft Corporation's plant near Bristol. But never has there been such an expensive bird before, nor one that has been so reluctant to fly. When she's ready to fly, she'll fly. Nothing must be left to chance. Concorde is unlike any other aircraft. Everything about her is new.
In the wind tunnels, the OG wing passes with flying colours. Full-scale mock-ups are constructed in order to show all of this SST's components. The drooping nose, a distinct feature of the Concorde, is built in order to balance pilots' visibility with its incredible aerodynamic structure. And using a converted Vulcan bomber, the Olympus 593 power plant is tested in the skies. For Concorde's team of designers, its engines proved to be the most important obstacle to overcome.
The airframe was in advance of the engines and in advance of the fuels at the time. Had you had 10-year advanced engines to put in it, and you might have possibly made it a more sustainable airplane. But as it was a prestige airplane.
For the 593's jets to work properly, air needs to enter at subsonic speeds. A huge roadblock, considering the Concorde is built to fly at twice the speed of sound. Fortunately, over a period of 4 years, a complex system of inlet doors and ducts are installed in order for this SST to travel at Mach 2. By April of 1966, the final assembly of 001 and 002 begins. With each country producing different parts of the Concorde, they're shipped across the Channel in order to make sure both prototypes are ready at the same time. Massive transport aircraft are used to ship some of the biggest pieces of this giant jigsaw puzzle. For the people of Toulouse and Bristol, seeing specially designed trailers hauling different parts of the plane are not uncommon during this time. And by December of 1967, Concorde 001 makes its first appearance in Toulouse. Its mesmerizing design stuns the entire world as aviation enters a new, high-speed age.
Toulouse. The giant hangar at Sud Aviation's headquarters was the focal point of the entire world. For inside was the most exciting new thing in the world of aviation, Concorde 001. At last, the Anglo-French brainchild, born out of the technical and very sensible collaboration of two nations, could be shown to an envious world.
While Concorde is being set up for its first test flight, in Moscow, the Communists are able to beat the Europeans, debuting Tupolev 144 on New Year's Eve 1968. Being almost identical to the Anglo-French design, it's nicknamed Concordski around the world. Unfortunately for the Soviets, it's nowhere near the Concorde in terms of structure and quality, being put together so hastily.
And the Russians ran into even worse problems with their version of it because their engines were comparatively far less efficient than the Rolls-Royce and the French engines.
In America, delays and uncertainties about their SST program continue. A competition between Boeing's swing wing and Lockheed's fixed wing design causes the selection committee to debate endlessly the advantages and disadvantages between the two.
It turned out that the swing wing didn't work, so they went with the fixed wing. Then it turned out that this plane was going to be too heavy anyway, so they tried to lighten it. But it could never really, the only way it could pay for itself is it couldn't really carry that many people, but secondly, because it was so heavy, it would have to charge a premium on the ticket, and that made the economics go haywire.
When the decision is finally made in the winter of 1966 to award the contract to Boeing, the Concorde already has a 2-year jump on its transatlantic competition. For the Europeans, a far more important threat to the aircraft's survival comes in the form of a jumbo jet. Boeing's 747, a subsonic airliner capable of flying passengers across the ocean far more cheaply than the Concorde, has those in Britain and France worried.
And in a sense, the Boeing company and airline companies as well understood that this was the real vehicle for leadership in commercial aviation. The jumbo jet, the 747, efficient subsonic jets of a variety of kinds, these were the vehicles that were going to keep America keep leadership in America in commercial aviation, not the American SST project.
This fear is amplified when the British Overseas Aircraft Corporation decides to purchase the 747. Perhaps faster does not necessarily mean better. Despite these outside threats, as well as concerns about its growing costs, Concorde 001 is cleared for its first test flight in March of 1969.
Toulouse. The great supersonic jetliner was going to fly. A year late, millions of pounds over the estimated cost, and still a very big question mark. But on this day, a lot of those question marks would be answered. For Concorde 001, this was the chance to prove she was the superbird everyone had hoped and worked for.
Its maiden voyage is flawless, encountering no technical problems. For testing purposes, its undercarriage is kept down. In France, they can breathe a sigh of relief. 1 month later, across the Channel, 002 takes off, making another perfect flight.
You had to have really the true professionals here. There's no point in the flight in which any kind of a crew error couldn't have caused a disaster. So it was a great leap forward. We didn't have the advanced electronics that we had later. And so for its day, it was really an advanced machine.
Concorde 002 is clear takeoff. And good luck, gentlemen.
For the next 2 years, a series of grueling tests are done, studying the impact that intense heat has on the nose and body of the aircraft. In the sky, Concorde proves easy to maneuver, as the two prototypes exceed both the speed of sound and Mach 2 during this time. Every detail is checked and double-checked, with nothing being left to chance. In America, with growing protests over the environmental impact of these planes, including the effects of the sonic boom, in 1971, the United States Senate votes to cut off all funding for Boeing's SST.
Good evening. The Senate has voted 51 to 46 to cut off money for building the supersonic transport, as the House had done before. Unless private financing is forthcoming, the controversial airplane appears doomed.
With this catastrophic decision, Concorde's most fierce competition is eliminated, clearing the way for it to dominate the global marketplace. In Britain, the plane becomes a symbol of pride.
It was a proud sight. This was the day when the traditional and the modern were brought together. The British Concorde, that masterpiece of technology, came to London to be seen by the Queen, her family, and the millions who looked up with excitement for a first glimpse of this great plane.
Then, in 1973, at the Paris Air Show, a Soviet Tupolev 144 crashes for the entire world to see. This disaster raises great doubts about the communist concoction's feasibility. It appears Concorde has all but won the race to build the first fully functioning SST. Now, will anybody want to buy the plane? After nearly a decade in development, the Anglo-French Concorde flies to the African nation of Senegal to begin its worldwide promotional tour. The ultimate goal of this exercise is to convince the world's airlines that speed means business. And with the right dose of public relations, executives will be convinced to buy these planes. From a marketing standpoint, the tour is an outstanding success. For years, people across the globe hear stories about this new high-speed plane that takes passengers to their destination in half the time. Its unorthodox aerodynamic design brings in crowds from Rio de Janeiro to Beijing, from Tehran to Sydney, from Fairbanks, Alaska to Mexico City. And with America cancelling their SST program in 1971 and the Soviet Tu-144 in shambles, the Anglo-French Concorde is destined to dominate the marketplace. Unfortunately, with the 1970s being defined by an oil crisis and economic unrest, the enthusiasm for a supersonic transport is a far cry from the previous decade, when anything seemed possible. The question now is, can this aircraft defy the odds by flying passengers around the globe in record time while remaining economically viable? This becomes the Concorde's greatest challenge. Across the globe, Concorde is ready to galvanize the people. Wherever it flies, the crowds are huge, anxious to see the plane they've heard about for years. During the year 1972, this SST tours Iran, India, China, Japan, and Australia, with each country's airlines showing interest in the aircraft. Kings and queens, prime ministers and presidents, rich and poor, all want to take a tour inside this remarkable supersonic jet. Unfortunately, during the 1970s, with each Concorde costing a record $31 million per plane, only the very wealthy are able to board this aircraft. Ironically, its biggest supporters are the masses, who could never afford to fly supersonic. As a result, although there's a fascination with the Concorde, the big airlines are hesitant to pull out their checkbooks. The Chinese and the Iranians flirt with the idea of buying them, but are unwilling to sign on the dotted line. In the United States, where the most lucrative destinations are to be had, President Richard Nixon tours the aircraft. His country's decision to cancel their own SST is the result of a growing environmental movement, warning Americans about the ecological disasters these planes will have on their neighborhoods and communities. A big drawback is the sonic boom. When a plane exceeds the speed of sound, a large noise capable of breaking windows and glass erupts. When scientists study the effects of this boom in Oklahoma City during the year 1964, they conclude this noise will cause a public revolt.
It turns out that the sonic boom, in fact, bothered lots of people. And this was clear very early on when they started to do research on the sonic boom in Oklahoma City. And a report came out in 1964 which showed that a huge majority of the people, quote, could not live with a sonic boom, unquote.
And the people who live with it are becoming more aroused, becoming more sensitive to this form of pollution as they are to so many others. The nation's priorities are changing rapidly, and the FAA may find that the general public has a different timetable in mind for the reduction of noise pollution. David Culhane, CBS News, New York.
It's such a hot-button issue that the United States government places a ban on all SSTs traveling coast to coast. With this decision, Concorde is limited to only the east and west coasts in America as destinations. As a result of this policy, no American airline wants to touch the plane.
Once that killed the New York to LA route, the Miami to Seattle routes, the Boston to San Francisco routes, the Washington to LA routes, once it killed those routes, it killed about a third of the market for the whole aircraft. And therefore you didn't have as much chance to recover your cost.
People in the United States reacted to the sound barrier as a means of going against the idea of an American supersonic transport, and it of course affected the issue of the Concorde flying in the United States. But I don't think it was a defining decision. And I also think it was a bit of a red herring. I think it was put up mainly because people who were smart enough to see there was no way to make any money out of the Concorde. Building it, the manufacturer was going to lose, the government was going to lose. I think it was perhaps overinflated just so that we wouldn't do it and we wouldn't have an American contender.
As environmental groups gain strength, pickets and protests against the SST's sonic boom, against its unhealthy fuel consumption and against noise pollution in general take place. Rumours begin that any passenger who boards the plane will become violently ill. This bad publicity sours the Concorde's reputation. Thankfully, the two countries who built the aircraft come to its rescue. When British Airways and Air France order 9 planes for service, they save the entire project from economic collapse. Unfortunately, the overseas buyers needed to make this a worthwhile government investment never materialize. What began as a European project is confined only to Europe. Despite these roadblocks, Concorde continues its worldwide tour de force. To prove it can fly in the most brutal weather conditions, the aircraft stops in America's Arctic outpost, Alaska, demonstrating that this SST can excel even in the bitter cold. Next is a flight to the polar opposite, Mexico City, where thousands of people wait for hours to see Concorde's grand entrance. With orders placed, the employees of BAC and Aerospatiale begin building more SSTs, improving the quality from the original prototypes. The Bristol 593 engines gain strength, reducing the black smoke emitted. And in 1975, Concorde receives its Certificate of Airworthiness. When agents are first allowed to book passengers, demand skyrockets.
A beautiful airplane that performed well. I was lucky enough to fly on it on one occasion, and it was the way to travel. There's no question about it. You arrived in London in what seemed like a couple of hours, and feeling excellent.
Although 20% more expensive than subsonic travel, during the early years, with all the hype and fascination surrounding this plane, the people cannot resist the opportunity to fly supersonic. 1 year later, the first 2 Concordes carrying paying customers depart from London and Paris simultaneously. Almost a decade after its first test flight in 1969, the dreams of this SST are finally realized. Concorde is given a boost when its only competitor, the Soviet Tu-144, fails miserably. Its crude design and enormous fuel consumption fades quickly. Only a few months of novelty flights take place, clearing the way for the Anglo-French. Despite this early success, the road ahead for this powerful new plane is going to be a bumpy one. In America, the Boeing 747 jumbo jet proves to be Concorde's greatest competitor, carrying more than twice the passengers at a fraction of the cost. In the Big Apple, where the most profitable route of London to New York is crucial, because of noise pollution, a judge rules that the supersonic airliner cannot land in the city. Over in Britain and France, many speculate that because the United States could not get its SST up in the air, sour grapes causes America to punish Concorde as a result. Only after a Supreme Court ruling is the aircraft allowed to land at JFK International Airport in 1977. Almost 20 years later, it would set the world record for transatlantic flight, travelling from London to New York in less than 3 hours. By this time, however, with rapid inflation, an oil crisis and growing environmental concerns, people begin speculating that this plane's time in the sun has passed.
People would pay the additional cost to fly faster than the speed of sound. However you valued your time, 1 times the value of your time, 1.5 times the value of your time, that's what people thought. It turned out, in fact, that this was a very questionable assumption. The whole idea that there would be a market for people paying a premium to go faster than the speed of sound on commercial aviation, in fact, was a facade. It turned out to be a facade. It was not true. It was a mirage.
During dire economic times, Concorde is viewed as a plane only for the super rich.
The clientele was superb. I mean, there were really, really rich people flew it. I can recall on the one flight that I made, there was a group of about 5 or 6 kids, all in one family, who were making their 15th or 16th Concorde flight and were totally blasé about it. So it taught me that, the Concorde was for rich guys.
The novelty effect has worn off. The enthusiasm of the 1960s, when it was first built, is replaced by the cynicism of the 1970s. Each year it's in service, Concorde fails financially, unable to turn a profit. As the 1980s begin, many feel this technological marvel's days are numbered. However, it's miraculously saved when British Airways decides to buy its planes from the government outright. With this decision, a new marketing campaign is launched to bring Concorde back to life. Discovering that its rich clientele are willing to pay more to fly supersonic, prices go up exponentially, making it a vehicle exclusively for the super wealthy. As a result, it's marketed as such, and for the next 2 decades, the plane stays afloat. Then, after more than 30 years, Concorde Flight 4590 crashes, raising doubts on the safety of supersonic flight. With the terrorist attacks of September the 11th, 2001, and the decline in air travel that follows, both British Airways and Air France decide to cancel service of the Concorde. In the end, the aircraft became a mixed blessing.
I think that the Anglo-French Concorde project may have been a model that showed the Europeans that they could collaborate in aviation. And while the Concorde itself was not successful, it may have been an impetus toward forming Airbus, which has been relatively successful in building aircraft and becoming a formidable competitor to Boeing. So in some ways, although the Concorde itself was not successful, maybe it was a catalyst or vehicle to create a successful, larger enterprise called Airbus.
Without question, its ability to travel at twice the speed of sound made the plane a first-class attraction wherever it landed. Over a period of several years, Europe's finest produced a true technological marvel, epitomizing the very best in engineering and aerodynamics. For those reasons, Concorde goes down in the history books as one of the greatest aircraft ever. In Britain and France, it was more than just a plane. It came to symbolize a time when they, and not the Americans, were at the top of the mountain. Just as England had ruled the seas with their dreadnoughts, they would rule over the skies with their Concorde. But with all its state-of-the-art capabilities, it became out of reach for the average man, woman and child, who, ironically, became the Concorde's biggest supporters. With the dim realities of the 1970s, the plane's biggest obstacles were not in its jet engines, nor in its payload, but with a skeptical public, who grew cynical at the idea of government and big business teaming up to produce a plane that only the privileged and powerful could fly on.
It was a beautiful airplane, still is a beautiful airplane, and it's just a shame that perhaps it's sumptuary. Maybe you don't need to go supersonically, and obviously not enough people need to go supersonically to justify the market.
Now, with the ability to communicate in a matter of microseconds through the use of computers, the Concorde symbolizes a much different time, when the best technology available to see each other in person was the airplane. In this era, faster meant better. And in getting people to their destination, no aircraft has been able to surpass the speed of the Concorde.